Well, it is a giant. It was a lifetime. We didn't order it, and like we had an ice cream party. You got you want to have it. That's the other one. Okay, that's mine. 1 second, sure. Don't worry, I think he was in the like maybe like five. I'm going to get you total.
Okay.
And so I got to want to get it up that. Experiencing more of we're early. Say for the last at least another.
Yeah. Is he part of the press board?
Not part of. He's the guy named Falls from there. Hey, I got a story.
Okay.
He's at the sometimes
Okay. But he's not.
not on site. He hasn't been that. We only have one of them. He was sort of for young.
Is that, I don't know, is that one of them?
Yeah, but very much. It's sometimes. So we on that sense, a lot of personnel. Writers. Orders of divorce. But it's also that. Where do you like every day that? 9 for storing down flow. So it's a little bit.
Okay.
He's so patient. He's so doesn't know that very quiet. Like feel.
Like you think for
Yes.
I aspire to be like that.
He's very, very. So. Unless you want to do something.
No, that's understandable. That and me also. I found out when I saw the title of that. Knocked off the big one with the plate.
Okay, hi everyone. So I think I'm gonna try and start on time. Just because we've got a compressed afternoon, lots of stuff going on. So there's okay, I'll go through the schedule in a second. So I'd like to welcome you all to Responsible AI in the Natural Sciences. So thanks for showing up in person. And thanks to all the people on the Zoom webinar. And so this event is hosted by the AI Planning Institute, which is in the physics department at CMU. So I'm part of the physics department, and also by the Block Center for Technology and Society. And there's a responsible AI initiative there that you can check out online and find out what that's about. I'd like to thank the co-organizers who did the hard work. So yesterday, Carson and Patrick, and also Patrick at the back, another Patrick. So that they're responsible for lots of stuff, including we have ridiculous amounts of food, so please eat, and there'll be more afterwards. So anyway, okay, so you might be curious as to who signed up to the workshop and what it was aimed for. So I put here the subject areas, and we were trying to aim it to natural scientists, but also computer scientists and a mixture of people who do AI and people who use AI. And so you can see that we do have a lot of computer scientists, you know, out of the 600 people registered, there's maybe 150 or so, but there are also astronomers, biologists, people who do engineering, social sciences, and so on. And the split of attendees, you can see evenly between faculty and graduate student, and also researchers, postdocs, and other researchers in industry and academia. So anyway, so that's who the other people are. And, you know, if you're one of the 10 speakers today, you know, that's your audience, right? Okay, so here's the schedule. So there's not too much time for breaks, but a little bit. There's a schedule. You can see we have invited speakers that you can see their faces there. There's also some contributed talks at 2:45 p.m. A lot of people, we had 50 or so people who gave in abstracts, and they were all great, and we had to pick 4 to present, and so those people will present. Chamek, actually, the first one actually came here in person, so the rest I think will be online. Then there's the AI versus human contest after that. So if you haven't taken part, I encourage you to click on the link on the conference webpage. People submitted, we had more than 50 entries of AI and human generated content meant to be scientific, broadly interpreted. And then now in the discriminator phase, you can try and tell them apart. If you're in the top 3, you'll get a prize. Right now, I think the current leader is 72% correct. So if you think you can beat that, the contest is open. It has been open all weekend. It will stop at 4 p.m. just before Stein's talk. And then we'll have a discussion panel at the front towards the end with the invited speakers. And there are a lot of questions submitted, and then we'll have a reception. Okay, so I've used up 3 minutes. So the next speaker, Hoda, can have an extra 2 minutes. So if you want to come up, Hoda. So Hoda Hidari is she works in this very building, right, from CMU Machine Learning. She's head of the Responsible AI Initiative here. And she's going to talk about responsible AI, need for a stronger governance ecosystem. And we'll find your. That's a PDF version. Cassie, do you know where it's on the desktop? Maybe you can find it.
Seems to be working fine. Yeah. Okay. So thank you very much, Rupert, and all the organizers for organizing this very timely workshop. So my goal with this brief presentation is to lay the groundwork for the rest of the agenda today by providing you with a bird's eye view of responsible AI landscape today, connecting it to some of the applications of AI in natural sciences, and finally outlining for you what I think are the major efforts going forward. So the conclusion that I hope you draw from this presentation is that AI as a technology is still in its infancy, despite all the excitement around it. We have made some progress in recent years towards developing the necessary frameworks, tools and processes to promote responsible and trustworthy use of this technology, but we have a long way to go. Especially with the rise of generative AI models, we have entered relatively uncharted territory, and the biggest lesson we should carry forward with ourselves is the need for strong governance and accountability mechanisms. So before diving in, let me first clarify what I mean by AI and also offer several noteworthy applications of AI in natural sciences in my view. So many of you in this audience might be familiar with the examples listed on this slide, but today AI is utilized by scientists across a variety of fields to automate or speed up a wide range of tasks, from discovering new planets, materials, and drugs, predicting the properties of those drugs, and more recently, again, with the tools such as GPT-4 and large language model, they are impacting the scientific communication and review process. So the use of large language models in scientific communication and peer review will be a good running example to keep in mind as we go through this talk. And I should say that we will barely scratch the surface of this topic in this talk, but Professor Sigurdsson will dive deeper into the implications of large language models for scientific writing. So I promised that I'm going to offer a definition of AI. So some of you may know that, but coming up with a definition of AI that everybody agrees with is notoriously difficult. But for our purposes, it won't be a difficult task. These days, most AI systems that you encounter utilize the methods and algorithms developed in a subfield of AI called machine learning, which leverages observational data to improve computers' performance on some clearly specified tasks. For example, language models are statistical models built using large language corpora to determine the probability of a given sequence of words occurring. And given that model, you can always predict what the most likely next word is going to be. So let's put a pin in those basic definitions and examples for now and do a quick tour of the responsible AI landscape. So responsible AI, some people like to refer to it by trustworthy AI, AI ethics, and those who are focused more on specific principles such as fairness, accountability, and transparency like to refer to it as by the acronym FACT. But all of these to me refer to the same line of work, which aims to tell us what are some of the values and principles that we should make sure we our AI systems align with as we go about designing and deploying them. Now, there are so many guidelines and framework for responsible AI that I couldn't choose just one, so I decided to just show you this tool that is basically a global inventory of AI ethics guidelines. There are at least 167 different guidelines out there. And even though they vary slightly from company to company, from government to government, and so on, if you distill them into a set of principles and values, by and large, you will end up with a handful of principles, in particular, the 6 or 7 that I've listed here: functionality and efficacy, fairness and justice, accountability and governance, transparency and explainability, privacy and security, reliability and safety, and a smaller number also include diversity and inclusion as principles we need to adhere by. So obviously, I don't think anybody disagrees that these are important values, and ideally we want to comply with them, but the devil is in the detail. The key challenge is, how do we operationalize these? For example, how do we define, measure, and promote a value such as fairness, transparency, or reliability in real-world usages of machine learning? So let's take the issue of fairness and justice as an example, because that's my area of expertise, and I can give you a historic view of how things have progressed. So a couple of years ago, say in 2017, 2018, I would have started my talk with this slide. So you can see numerous media articles documenting and reporting the unfair disparities that the use of AI in socially high stakes domain could give rise to in a wide range of domains, from education to criminal justice and medicine. Now, stories that you see on this slide firmly established the need for the machine learning community to go beyond basic accuracy metrics and traditional evaluation paradigm if our goal is to utilize these tools in social domains. For example, in medical applications, if you're trying to do the patient diagnosis or prognosis, we must carefully define and promote fairness and non-discrimination, and ensure that the machine learning models we train do not adversely impact already vulnerable patient populations, for example, those who have a rare disease or those who have relatively lower access to the healthcare system. Now, early on, the work in this area focused on offering mathematical formulations of fairness and algorithmic interventions to guarantee those mathematical notions of fairness. My own work in this area focused on bridging the gap between these formal definitions and concepts such as distributive justice, equality of opportunity, welfare inequality, and beyond from political philosophy and economics. Now, all this work that I'm alluding to here focused on fairness as a form of parity in outcomes or a form of distributive justice. It did not get at procedural and social justice considerations, which might be much more salient and consequential for stakeholders. But let's bracket that for the moment and suppose that outcome disparities are of highest importance to alleviate. This is, I argue this is rarely the case, but let's go with it for now. So how should we alleviate outcome disparities? So to make things concrete, one very common notion of outcome fairness is the so-called demographic disparity, the idea that the model we train should make the same, should lead to the same selection rate across different socially salient groups. For example, if you're in an employment context, we want to make sure that if the rate of calling female applicants to interview is 80%, we want to make sure that the rate for male applicants is roughly equal. So how should we make sure that these notions are satisfied by the model we train? Does it suffice, for example, to add a fairness constraint to our risk minimization pipeline and make sure that the model satisfies those notions through these constraints? So the short answer is no. So over time, the community has realized that ideally we should trace back the disparity to its root causes in the machine learning pipeline and intervene at the right point, usually at the source. For example, if the cause of the disparity is in the data, we probably want to fix the data as opposed to adding a fairness constraint to the risk minimization pipeline. So that area is still a very much active area, and my own research contributes to it. And zooming out even further, what we have started to realize as a community in the FACT community is that it doesn't suffice to just understand the machine learning pipeline and how we can have various biases creep into it at different stages. We also need to understand machine learning embedded in its complex social and human context. So the machine learning pipeline is often interacting with numerous social entities and stakeholders who may hold competing goals and values. So here is a very simplified image I've put together to organize these interactions for myself. So some of the key stakeholders to keep in mind are designers and creators of AI or machine learning systems, decision makers or users of those models, people who utilize the predictions the machine learning model makes and do something with it. Decision subject, those who are impacted by the decisions made through the use of machine learning models, and finally, oversight entities. So in the context of the use of AI in natural sciences, the users might be the scientists who utilize these tools to make different types of inferences. The decision subjects might be people or even future generations whose life will be impacted by the kind of scientific discoveries we make. So I hope this gave you a very high level chronological tour of the fair machine learning literature. So we started out focusing on mathematical definitions, narrow mathematical definitions. We realized very soon that that doesn't suffice. We need to think about sources, what causes these, and then we realized those causes are not always algorithmic and something that we can fix in our data and algorithm, but rather we need to take a more holistic view, look at the system as a socio-technical one. Now, I think that many of the lessons that we learned from this fairness journey are going to be applicable when we are thinking of different types of AI and when we are thinking about different principles. So if I want to distill some what I consider to be some of the main lessons we have learned from this the way the literature on fairness has progressed, I would say here they are. So the first one is that we need to clarify the purpose of using AI, and we need to be able to say exactly what is the value added that we think AI is offering. We need to verify functionality. Just because we are excited about the use of AI doesn't mean that it actually works. Oftentimes you see in practice that the cause of all sorts of misalignment with our values is that the AI actually doesn't even work, right? If something doesn't work, there is no way that it can align with our values. We need to understand stakeholders and their values. Usually, the designers of these systems are not trained to think about other perspectives, other values, and other views, and that's very important. We need to be able to better imagine and measure potential impacts, in particular negative impacts. And we need to be able to trace them back to their root causes and try to address them properly. We shouldn't just assume that because we are observing some kind of a disparity, for example, at the end of the machine learning pipeline, this is an algorithmic problem that we can fix. And finally, I think it is important for us to develop processes for governance throughout the AI lifecycle. And I will come back to this briefly. So one thing I want to mention again is that I think the same lessons apply to different principles. For example, if you're thinking about transparency and the operational and operationalizing it via this idea of coming up with explanations for model predictions, we need to keep the same considerations in mind. And I believe Professors Lakkaraju and Tofty will tell you more about the nuances of explainability as one principle we may want to aim for. Okay, so I don't have much time left, but let me try to tell you a little bit about large language models because I promised at the beginning. So if you fast forward to late 2022 and 2023, and the rise of generative AI models, which took the world by storm. I'm sure all of you have heard about ChatGPT, GPT-4, and BARD. As I mentioned, this is while many of the lessons we have learned are hopefully applicable, this is still uncharted territory, in part because this is a relatively new paradigm of learning, and we have limited access to to many of the decisions that have gone into these kinds of models. So what are large language models? Again, as I mentioned, large language models are basically statistical models that try to predict the most likely next word, right? That's all that it is. So it doesn't these models don't necessarily have a concept of language. They don't necessarily understand the human language. They are just trying to predict, given what has been uttered so far and what I know, but what I've seen in the usages of language before, what's the most likely next word. So, and I argue that despite the excitement recently, we have all seen large language models before. For example, when for many years now, we all have seen autocomplete in search. This is one example of language modeling. So large language models such as ChatGPT are clearly very impressive at a first glance, and I think it is okay for us to be optimistic about their potential. But if we are using them in a clearly scoped, for clearly scoped tasks. So the tasks that I think are good candidates for use by LLMs are those that are well structured and they allow for quick and low cost human oversight. For example, if you think about the task of writing a code to develop software, it satisfies these criteria. It is very easy to quickly, you can run the code and see if it works, if it gives you the results that you want. Whereas I would argue if we are using it for summarizing a literature or for distilling the key findings in a literature, I am much less convinced that the technology is at the point where it can achieve that. And I will tell you in a second why. So just in the past couple of months, we have seen ample evidence that if utilized haphazardly, the use of large language models can give rise to or amplify a variety of harms, including hate speech, exclusionary language, misinformation, malicious uses, socioeconomic harms, in particular environmental and employment-related harms, human-computer interaction harms, and beyond. Now, I argue that these risks stem from technological limitations, lack of sufficient safeguards against inappropriate use, lack of transparency and accountability for harms, and economic incentive to misrepresent capabilities and opportunities. So let me just show you very quickly a couple examples. I won't have time to go over them, but I would just want to mention that these language models fail very basic common sense reasoning tests. In this particular example, someone asked ChatGPT, the trophy didn't fit in the suitcase because it got too small. What was too small? And it goes on to confidently respond that the trophy was too small. Now, as a human, this for us is a no-brainer, right? So despite the vagueness in the statement, because we have contextual understanding of the world,
we can quickly figure out the trophy was too large. That's why it didn't fit in the suitcase. Factual errors or hallucinations is another major issue with large language models. They can generate content that appears legitimate but has no basis in reality. Here you can see someone asked ChatGPT to produce references for an answer it gave to a question, and it generated references that look like legitimate scientific references, but none of them are actual papers. And it is noteworthy to, it is notable that these are actual people, actual academics, right? But the papers are not their papers. Now, I hope these examples go to show that you should really think twice if you're thinking of utilizing large language models for doing any part of your research process that requires analytic thinking. For example, if you want to do literature review or if you want to write peer review, that's one area that I'm very concerned about. And so while the creators of these systems have put in some safeguards, it is very easy to jailbreak those safeguards and get these language models to produce language that we, for a variety of reasons, may wanna avoid. So I think in addition to the technical limitations, we should be cognizant of the complex socioeconomic incentives and power dynamics that surround the development and release of large language models in recent months. And we need to keep in mind that only a handful of big corporations can produce these models, and they have full control over all the choices that go into designing, developing, evaluating, and marketing them. And they don't really face any responsibility or liability for harms and misuses. For example, we saw that we saw the example of a man who killed themselves after interacting with ChatGPT as a counsel. So who is going to first consequences for that? So this is all to say that we need more robust governance mechanism in place to align practices and incentives with responsible R&D and use when it comes to large language models. Fortunately, we are witnessing lots of activity both at the state, federal, and international level. And I think one contribution we can offer with our expertise is to seriously engage with policymaking efforts and ensure that they reflect the state of the art. But can we do more in settings where we have more power and control, namely in higher education and in research? I argue that, yes, there are a couple of concrete recommendations that I would like to end my presentation with. In the context of education, I think it is important to develop responsible AI courses that demystify the technology and highlight its limitations. In terms of research, I think it is very important to encourage investment in low-risk, high-reward use cases and develop standards and best practices for responsible design and development of these technologies. And when it comes to large language models, the issue of evaluation is particularly challenging, and we are, and this is a wide open area of research. And finally, when it comes to policy, I think fostering a productive partnership between the academy and policymaking entities would be fruitful for both sides. So that's it. I think I ended with 40 seconds, so I may be able to take one question.
Okay, thank you. Good. So yeah, while we're setting up the next talk, maybe somebody has a question. There's one online as well. Sure. Yeah. Okay. Go ahead.
Yeah, so there's a question online from one of the attendees that says, how would you counter the argument that some people in corporations are not having AI guidelines?
I didn't quite hear the question. Some people in the industry are what?
They were saying there some people in corporations may not in the end strive for the ethical, so well, how do the AI guidelines line up with their priorities?
So I think even if we take that the premise that in the industry people are only concerned with the bottom line, I think the pressure from the public is important to make the alignment with our values and principles a part of the bottom line. So I think it is important to continue this work and push for adhering to these principles. Great, thanks.
It froze for a second, but we can make this. They are on the other end, ready to present.
Okay. So our next speaker is Hima Lakkaraju, Professor Hima Lakkaraju from Harvard Business School. And she's going to be talking to us about explainable AI, and she's remote. So Hima, you can share when you're ready, your screen.
All right, okay, let me just share my screen first.
Okay, yeah, we can see you now.
Okay, all right. Okay, hope my
Okay,
screen
yeah,
is good.
Go
All right.
ahead, we can hear you.
Okay, awesome. Thanks so much, everyone, for joining me today, and thanks, Rupert and other co-organizers for putting together this very interesting and insightful workshops. So today I'm going to be actually furthering from what Hoda Haidari was talking about just now and focusing more on explainability, or more broadly, right to explanation. So the title of my talk, as you can see here,
Sorry.
is Enforcing. Oh, hello.
You're back now. Thank you.
Oh, okay, great. Yeah. So I was just saying that the title of my talk for today is Enforcing the Right to Explanation. So what are some technical challenges, solutions, and opportunities here? Okay. All right. So let me start this conversation by first highlighting some of the details about right to explanation outlined in several policy documents and regulatory frameworks, right? So for example, if we look at Recital 71, Article 22 of GDPR, you find a sentence that says something like a subject has the right to an explanation of the decision reached after algorithmic assessment, right? And when talking about this kind of a right to explanation, a lot of regulatory frameworks and policy guidelines do try to contextualize it in the context of domains such as finance, law, and healthcare, because that's where you see a lot of high stakes decisions being made on a day-to-day basis. Right. So going further, so Hoda again flagged one of these blueprints for an AI Bill of Rights, which was outlined or put forth by White House and Office of Science and Technology Policy in the US. And they have a specific section called as Notice and Explanation, which basically has this line which says that you should know how and why an outcome impacting you was determined by an automated system. Right. So clearly, there has been a lot of emphasis on sort of understanding how models are making predictions, or more broadly, if we were to put a phrase to that, right to explanations in a lot of recent policy guidelines and regulatory frameworks that have been put forth. Right. So let's try to understand how recent literature in machine learning and beyond has tried to interpret some of these guidelines and how they look when they're in action in practice, right? So for example, we could see this scenario where we are sort of looking at a law or a criminal justice based scenario where there is a defendant who is being sort of judged for with respect to if they should be granted a bail or not. And in such a scenario, if we have a predictive model ingesting the details about the defendants and predicting if this defendant is risky to release or not, then such a tooling, and if a judge is actually at the receiving end of such a tooling, as opposed to sort of just giving a decision or an outcome for this particular defendant who is at the receiving end of all of this, right to explanation in some sense is trying to enforce that the defendant should also be provided with an explanation, which could take this form, for example, where in this case, the defendant may be told that features such as past crimes or failure to appear in past court cases, as well as active cases, all of these are basically, driving the outcome for this particular defendant, which is that this defendant might be too risky to release, right? Another scenario could be that of a loan application, where a bank may be employing predictive models to determine which applicants should get loans. And in this case, again, there is a predictive model which is ingesting details of a loan applicant and predicting whether the person should get a loan or not. Instead of just leaving this workflow at this, right to explanation is actually trying to ensure that the loan applicant gets more information. For example, what can he or she do in order to improve their profile, come back, reapply for a loan and get it, right? So for instance, in this case, the applicant may be told that they need to increase their salary by 5K, pay credit card bills on time for the next 3 months, and come back and reapply for a loan. right? So this is how a lot of research in machine learning and beyond has tried to envision right to explanation being enforced in practice, right? In order to enable these kinds of explanations, there were several approaches that have been put forth in the literature. I'm going to sort of characterize them into two very broad categories. The first category is to build models that are inherently interpretable. So for example, models such as regressions or shallow decision trees or simple rule-based models like rule sets or rule lists, all of these prior literature has actually argued that they could be considered interpretable because we could look at these models and roughly figure out what the model is basing its decisions on based on either the weights put on each of the features or based on the features that show up in a shallow decision tree and the decision paths, right? So that's one way in which right to explanation can be operationalized in some of the real world applications. Now, the other approach that has become popular since about 2016, that's the last 6 to 8 years, is to build models and explain them in a post hoc fashion. So what do I mean by that is you could have a black box model, or you could have a really complex model like a deep neural network with several hundreds of intermediate layers. Now you can build these explanation methods or explainers which ingest these kinds of complex models and break them down into simpler models that are more easily understandable to human end users or domain experts who are not necessarily experts in machine learning, right? So these are the two very broad strategies that have been employed in prior literature. And oftentimes, whenever we mention that there are these two broad strategies, the immediate question that pops up is, when should we use interpretable models, inherently interpretable models, versus when should we rely on post hoc explanations, right? So the answer to that basically lies in some of the pictures that I'll be showing on this slide. So one of the first reasons for even the advent of post hoc explanation methods and reliance on post hoc explanations is what can be shown, what can be seen in this particular graph, right? So a lot of recent research actually showed that there are trade-offs between interpretability and accuracy, especially when your data is huge and or is high dimensional. So which means you might see models such as linear regressions or decision trees or logistic regressions performing very highly when it comes to interpretability, but they are not as accurate as models such as deep neural networks, right? But the issue is that models such as deep neural networks, while they are accurate, they are not very easily interpretable, right? So this is why there has been a lot of focus on using post hoc explanations so that we can try and get both accuracy and interpretability. Another reason is a lot of models, as you can see again with the coming out of all of these large language models, a lot of these models are actually proprietary and we really don't have any access to the internals of these models. In such a case, the only option that we are left with is to basically resort to or rely on post hoc explanation methods, right? So that's why the strategy of post hoc explaining existing models, whether they're black boxes or complex models, has become very popular in the last few years. And in the rest of this talk, I'll be focusing on post hoc explanations as I present some of our work. Okay. All right, so let's go back to this example that we started at the beginning of at the beginning of this talk. So what we are seeing here is, again, we are in the context of law. And here, as opposed to just telling a defendant that, they are being given a negative outcome, providing them with an explanation for what are the features that drove that outcome could be very helpful, right? So that's the scenario we are talking about. So how to even generate this kind of an explanation where we say things like the top 3 features driving this prediction are so and so. So in order to do that, there is a huge class of popular explanation methods referred to as feature attribution-based local explanations. And I'll explain each of these words to give some intuition about them. So local explanations, as the name suggests, are focusing on explaining individual predictions of any given classifier. So we are not trying to explain a complete model. We are instead trying to explain individual predictions of a given classifier. And all of these methods, that is the feature attribution-based local explanation methods, they output feature importance scores for individual instances such that each of the feature importance scores captures the effect or contribution of a given feature on the black box prediction, right? So basically what these methods output is a vector of feature importances, one for each feature, that explain the prediction at hand, right? A single prediction at hand. So you might have heard of methods like LIME, SHAP, gradient times input, smooth grad, and integrated gradients. All of these are popular methods under this category of feature attribution-based local explanations, right? So far, everything seems to be going good. We talked a little bit about what the policy guidelines are suggesting. We talked about some of the solutions the machine learning community has put forth. So where is the problem, right? So the problem is that we'll talk about multiple challenges, but the first problem that we are going to discuss is that despite the existence of several methods which claim to explain individual predictions of machine learning models, there are some challenges, such as there are disagreements between these methods, and there is also a lack of standardized evaluation, which is driving some critical problems, or which is causing some critical issues in the practical usage of these methods. So in order to understand this better, I'm going to discuss one of our recent works where we carried out extensive user studies and empirical analysis to understand if and how often these feature attribution-based local explanation methods disagree or agree with each other in practice, what constitutes disagreements between them, and how to formalize this notion of disagreement based on practitioner inputs, and how do practitioners resolve explanation disagreement, right? So a lot of this work was born out of our interviews with practitioners who were using these methods on a day-to-day basis, and we asked them to describe what are the challenges they're facing with these methods. The immediate problem that sort of popped out at us was this problem of these methods disagreeing with each other. So what we did here was we did 30-minute semi-structured interviews with 25 data scientists, and 84% of these participants actually mentioned that they would typically run multiple explanation methods whenever they were trying to determine what features are driving a prediction. And unfortunately, they often ran into scenarios where these methods disagreed with each other. When we asked them what exactly do they mean by disagreement, they gave the following explanations. So the first one is the top K features output by different methods as the drivers for a prediction are often different. And in some scenarios, while the top K features are similar, the ordering among them is different, or the sign of the feature contributions, whether it is positively contributing to a prediction or negatively contributing to a prediction, those are different. And of course, relative ordering of certain features of interest is also different, right? So their problem was that the high-level insights coming out of the explanations produced by various state-of-the-art methods are actually not in sync. They all give different insights. And we then tried to probe this problem of, okay, so clearly they're running into this problem. So what do they do to resolve disagreements? And in order to understand this, we conducted an online user studies where 25 users, again, who were data scientists, were shown explanations that disagree with each other according to their own notions of disagreement. And we asked them to make a choice as to which explanation would they pick, and also explain why they would pick that explanation. And what we found was actually something that was quite alarming. We started realizing that practitioners are choosing a particular explanation method and its corresponding explanation, and they're basing these decisions on ad hoc heuristics. For example, we saw some quotes talking about the fact that I'm picking this method, I trust it more because that paper has more theory. Or I am going to pick this method and trust it more because it's more recent. Or I'm going to pick this explanation because it just matches my intuition better. Or in other cases, it's the type of the data. Some methods are better for tabular and others are better for images and so on, right? So though that was not really established as the case. So what we see is that practitioners are really relying on a lot of ad hoc heuristics when resolving these disagreements. This highlights a critical problem that they may in fact be relying on incorrect or misleading explanations when making decisions in real world applications, which is a problem, right? Okay, so what is all the study and what are all these insights telling us? So they're telling us that these methods often disagree in practice with respect to basic insights they provide, and practitioners are resorting to using ad hoc heuristics to resolve these disagreements. So now the next questions that arise immediately are, why do these methods even disagree? Because they're all supposed to explain the behavior of a model or explain a prediction of the model, right? And given that these methods disagree, which methods should we choose for different kinds of data and applications? What are some guidelines for that? And in order to probe these questions further, we did more theoretical analysis, and we kind of showed that a lot of these feature attribution methods are in fact essentially performing local function approximations. So that's what they're doing, but they differ in the fact that they employ different loss functions and different definitions of local neighborhoods when they perform a local function approximation to approximate the underlying model, right? So there are some similarities, but there are also some differences which explain all these disagreements. And in order to sort of move forward and figure out which methods to choose given these disagreements, we propose two solutions. The first solution is perform theoretical analysis to understand which methods can effectively recover the underlying model and under what conditions. And in fact, based on this analysis, we provide some guidelines that if your data has continuous features, certain kinds of methods will completely recover the underlying model under certain conditions. Whereas if your data comprises of binary variables, then you may want to rely on other methods. And our second solution was to develop this sort of an extensive benchmark which allows all the folks, whether machine learning researchers or practitioners or even researchers in other communities, to evaluate and benchmark different post hoc explanation methods and assess their quality. And we employed a bunch of different metrics in this evaluation framework, which focus on evaluating the correctness or faithfulness, stability, fairness of the explanations produced by state-of-the-art methods. Okay. All right, so I'm going to, in the interest of time, I'm going to very briefly touch upon this, but try and conclude very soon. So the second bigger challenge beyond the disagreements and lack of standardized evaluation is the trade-offs that occur when we try to operationalize different regulatory principles. So what do I mean by that is, for example, there may be trade-offs between right to explanation and right to privacy. In fact, one of our recent papers demonstrates that model explanations actually enable adversarial entities to infer which individuals were present in the training data of the model more effectively than they would without access to model explanations, right? So clearly there is a conflict between exposing more information about the model and protecting the privacy rights of the users who are part of the training data. Right. So a solution could be something like, let's train differentially private models, but there's a caveat that these kinds of models always impact predictive accuracy. So it's questionable whether we can use this as a solution in all settings. So similarly, one of our other recent works talks about the trade-offs between right to explanation and right to be forgotten. And what do I mean by right to be forgotten is that this is yet another one of the principles that is upheld in several policy guidelines and documents. So this basically allows individuals to request erasure of their personal data from databases and models of organizations. So you or I, as users of services of an organization, can say at any point that we are deleting this service and we want all our data to be removed, and the companies are supposed to comply with such a request within 30 days, right? So the interference between right to explanation and right to be forgotten comes as follows, okay? So when somebody requests erasure of their personal data, that typically triggers an update or a change in the model, which in turn may invalidate some of the explanations provided by the organization to some other end users, right? So thereby violating right to explanation. So maybe the organization already told an end user to increase their credit score or to increase their salary based on the previous model, but now the model has gotten updated because of right to be forgotten. And now the prior explanation is no longer valid, and now the user is left with something that's like no longer relevant, right? So how do we bridge these kinds of trade-offs? And we propose solutions which try to generate explanations that are robust to small changes in the model. Of course, this also is not a foolproof solution, because what if there are drastic changes in the models? What if, it's hard to generate explanations that sort of work with different models or are robust to different kinds of models and so on. So there are a lot more open questions. But basically, my point is we need to keep in mind that there may be trade-offs between the different regulatory principles that we are trying to operationalize in practice. Okay? So hopefully this talk has enforced that there is a lot of critical gaps. There are a lot of critical gaps to be bridged between policy and technical solutions when it comes to enforcing right to explanation as well as other rights. It's important to standardize the notions of what a model explanation is and also evaluation of these model explanations so that we can determine which explanations to trust, which ones to rely on, and also assess their quality. It's also important to understand and address trade-offs between different regulatory principles, for example, between right to explanation and other principles, as we just saw. And of course, with the advent of large language models, these models claim to be self-explanatory. For example, they provide the sort of chain of thought reasoning for the answers that they give, but it's unclear how reliable are these kinds of chain of thought reasoning based explanations. Do they really reflect models' inner workings, or are they just mentioning something so that an end user is happy with the predictions that the model is making? And it's also unclear what are the risks of relying on incorrect explanations produced by these models. So there are several open questions here that need to be investigated further. With that, I would like to thank you all for your time and also show the slide with some resources on the topics of explainability and other areas of trustworthy machine learning. Thank you so much.
Okay, that's great. Thanks, Hima. So while we're setting up the next speaker, Savannah, maybe if there's a question, remember, of course, we'll have a discussion panel later on, and Hima's going to be on that too. So if you have any questions, okay, so we've got a question from Stein in the audience, Stein Sigurdsson. There's a microphone somewhere. Patrick, do you want to? Yeah. Okay, hang on, you just bring in the microphone.
I think it was a very thought-provoking talk. One thing that popped into my head while listening is the right to be forgotten. If it is used for models being used for explanation, isn't there a danger that the updated model will be selectively biased, because presumably right to be forgotten is not activated randomly, but preferentially for some bad implied outcomes?
Yeah, no, that's a great question. Yes, I think there could be scenarios where the request for erasure of data may be coming in from certain protected groups, for example, right? So for whatever reason, a certain community feels that they need to withdraw from a service or from an online app or something, and then you may see people from that particular protected community just leaving, and that in turn may cause bias in the model. So as a consequence of right to be forgotten, you may see fairness issues arising. And in fact, we are trying to do some work on mitigating such issues in different ways, both by updating sort of the risk minimization frameworks, as well as like better data collection or relying on external resources. But you're absolutely right that right to be forgotten has other risks as well. One of them is perpetrating unfairness.
Okay, that's great. Thanks a lot. So yeah, we'll hear from you later for the discussion panel. All right, thanks. So we'll move on to the next speaker. It's Dr. Savannah Theis from Columbia University. And she's going to be talking to us about AI as an object of study. Savannah is a particle physicist and somebody who thinks a lot about AI and looks at AI as well. So,
Ooh, okay, let me make sure it looks good at the other end.
Can I not make it like be on the full screen?
There you go.
Okay, thank you. Yeah, so right, I'm super excited to be here and following two talks from people I really admire. So very excited about this. So I'm going to be talking, yeah, about AI systems as an object of scientific study and how we do science with AI. So like was mentioned, my background is originally in particle physics. That's what I did my PhD in, and I've been working in machine learning research for the last 4 years. And yeah, to sort of frame this talk, I'm showing here kind of 4 of the papers that have really impacted my recent work. And I struggled with what word to use here. So I have it saying AI has a reliability problem, but like we kind of saw in the 2 previous talks, I think you can substitute a lot of different words for reliability here. We talk about robustness, we talk about trustworthiness, fairness, all of these kind of things. But I think a lot of those issues we talk about come from similar places. And unlike some of the other talks, I'm going to kind of focus on technical and like scientific method components here that I think contribute to some of the issues we're seeing. And I'll say this caveat at the beginning that I don't want to present the idea that science and math are like the only way or the way to solve these problems fully. I think we need governance, we need explainability, we need participatory design systems, we need all of those things. But I'm a scientist, so I'm going to talk about the science side. But these are some examples of what I would call technical or scientific issues that cause some of these downstream consequences of biased systems, of negative social impacts. So we have things like the way that we even do machine learning research tends to be very focused on certain constructed tasks and benchmark data sets. So a lot of the publishing that we do in machine learning is, you only publish a paper if you get state of the art performance on a benchmark test like ImageNet, which helped revolutionize the way we do computer vision, and it led to all of these amazing deep learning driven advances. But there are limitations that come from that as well. And this paper is really great, and it talks about ways that sometimes the tasks and benchmarks that we design don't actually relate to what we want to do in the real world. We've already seen several mentions of this. A lot of times AI systems just don't work, right? Like there are different technical issues, there's data leakage, there's poor testing or neglected testing, bad experimental design practices. We try to use AI for things that it shouldn't be used for, like tasks where we have no idea of a mathematical model for it, like measuring trustworthiness or something. Like how can you we have no way to evaluate that, right? We don't have a mathematical measure of trustworthiness. So how can you evaluate a model that says it does trustworthiness prediction? Or even something, right? Yeah, like trying to apply AI to tasks or acceptance of, we just don't know how AI works, but it's fine. Like it seems to be working. So let's just go ahead and use it, even though we don't really understand it. I also think that AI has a big hype problem, right? Like we see just crazy things happening right now. Like every day I open the news, I open Twitter, and I'm like, what is going on? All of these very, smart, scientific, in theory, researchers are making these claims. We have AGI now. We have theory of mind and language models. We can use AI to fix bias instead of creating more bias. Like all of these things that I think are not super founded in rigorous study. And I think there's a real danger to this. We've already seen this in the first 2 talks. There's a real danger to treating something that on one hand, we conceptualize as being very scientific, mathematically grounded, to treating that as something that's superhuman, something that's magical, that we can't understand. And I kind of outlined 3 types of risk here. So there's present risk, like we've been talking about. There's risk to subjecting people to under-evaluated, under-tested, or just incorrect AI systems. We've seen how this can entrench bias in our society. It can automate bias in different ways, and it can also push responsibility for that stuff onto the people who use technology. Because if we, say like, oh, AI is trustworthy, it can do all these different tasks. If then you're harmed by it, it's easy for the people who build it to say, well, it's your fault. Like we tested it, or we put these caveats on how you should use it. You misused it. It's your fault that something bad happened to you. There's also a risk to our future societies, right? Designing a piece of technology, building a piece of technology inherently, presents itself as a solution to something. So by building the types of language models we're building, by trying to use them in tasks we're trying to use them for now, we are sort of removing ourselves from considering other solutions. Self-driving cars is a great example, right? Like by investing so much in self-driving car research, we are maybe pulling resources away from things like designing public transit or just more walkable, more equitable cities. But instead we get to build fancy technology, and that's fun, and science is fun. So like, we tend to ignore those kind of questions. And then, yeah, like was mentioned also in the previous talks, we risk entrenching power in systems that are not like designed to actually support us or to be democratic. We, by allowing more and more infrastructure functionality to be subsumed by AI, we are concentrating more power in the hands of the very, very few companies that can build the current types of scale models that we have. And it also affects the kind of research questions we ask, right? Like if we're all in on scale and building bigger models with more data, what are we not building? And so I've recently been kind of toying with this thing that I'm calling the empirical gap. So if we try to think about AI and machine learning as like a science, what kind of science is it? To me, it seems very different than, other types of science, chemistry, physics, biology, those kind of things. And there is like a space of theory kind of driven research in machine learning where people look at like statistical limitations of certain types of models. They look at scaling laws, performance of gradient descent, different optimizers that we use. But to me, there seems to be a big and ever increasing gap between what people are doing in that space and like what we are doing at the sort of cutting edge of AI that we're putting out into the public, right? Like we have no theory of large language models. We sort of know, okay, we know what a transformer is, but we don't know why it does better than anything else. Like we really have no theory there. So there's, right, what I'm calling this empirical gap where the kind of things we can get real theory-driven results for are so much smaller, they're so much limited than the kind of systems we're using in the real world. And I think that's very dangerous, and it's sort of an odd paradigm if you really think about it, right? Like we've entered this space where we sort of have no fundamental understanding of something that we've entirely constructed from math, right? So we sort of get this idea that we understand how it works and we should trust it. But if you ask someone, right, why ChatGPT does something, or even will it always do that? Or if I change the prompt slightly, will it do something else? Like we don't know. And I think that science can give us some ways to address some of these things. So I have sort of some different like scientific frameworks that I'll show here. So one is thinking about, if you're just building an AI or a machine learning model yourself for, a big portion of people in this room, probably some kind of science task, but also it could be for some kind of societally applicable task. So this is like a super simplified example, but it kind of shows how you might walk through like the traditional scientific method, but treating your actual AI design process as a scientific experiment. So I'm using an example here from my background in particle physics. So let's say I want to use machine learning to identify Higgs bosons at the Large Hadron Collider in Switzerland. And I want to frame that itself as a scientific experiment. So for getting the science part of doing a Higgs boson measurement, I want to think about my actual AI building as a science experiment. So I might make some hypothesis like, this one feature, the angle between the decay products of the Higgs is going to be a useful signal for my model. Then I'd go through the whole scientific method. I'd collect the data, ideally a data set that someone has looked at before so I can use it to compare to other methods. Then I would build one model using that as a feature amongst maybe some other features I've already thought about. That would be testing your hypothesis. Then you'd analyze your results. Does this work better than other systems? You need to have other things to benchmark it against. You need to have a comparison method that actually can compare performance between the two. And you often have to think carefully about that. And then you would reach some kind of conclusion like, I should or should not use this feature as a signal. And then you would refine and repeat from there. And that could be, you want to look at a different feature. It could be you want to try a different architecture. But this kind of shows how perhaps we should be approaching using machine learning a little bit more slowly than we are in some cases, and doing a little bit more of an iterative process where we test out our assumptions instead of just going like full force forward with everything. I also this is sort of a framework for thinking about impact assessment of our models as well. So maybe you're not building something to do Higgs boson identification now, maybe you're doing something, I don't know, to decide triage, to model triaging in a hospital, or welfare at system access, or something like that. And so again, I think we can think about this with a bit of a scientific mindset. So you can think about how the errors of our model and the harms that those errors might cause in the real world are distributed, and those things are not always distributed the same way, like we kind of heard in the previous two talks as well, right? Like a misclassification in a model is not necessarily like the harm that that model is going to cause. So they might be kind of separate things. But we can think about understanding those distributions as well in kind of a scientific lens, right? Thinking about how do those distributions vary across different, I say phase space because that's like a physics term, but phase space meaning different parts of the population, different geographic areas, different hospitals, like all kinds of different spaces, different demographic groups, thinking about, right, how your distribution of error and harm vary across those groups. And so I think you can start to map some of the questions we ask when doing scientific or physics analysis onto looking at these distributions of harms, right? So how did your data selection contribute to the final error distribution that you're seeing, right? Did you only collect training data from some part of the population? And so it makes sense that now our model doesn't work on some part of the population as well. How do you make sure that you're actually modeling your error and harm distribution correctly? What kind of tests can you use to evaluate that? What should the distribution look like? So thinking about the fairness definitions that we saw before, like what is our test world or our ideal world that we want to contextualize these distributions in? How should it look if we have a certain fairness goal in mind? And then what knobs or things can be changed if they don't look the way that you want them to be? How can you go back and adjust your model or adjust your data set in a way that helps make these look more like what you would want them to? And I think you have to think about this at all, steps of the kind of technical pipeline building, right? Your data collection, who you're taking it from, what it's collected, what format it's collected in, how you deal with missing data, how you deal with imbalanced classes. All of those things are going to affect the final distributions that you get. Processing, right, any kind of cleaning that you do, your model building, what features you use, whether or not they're related to the actual outcome that you want to model, how they're related, right? Are there causal effects that you don't want to capture, or you do want to make sure you capture? Are there statistical assumptions in the particular model you're using? Like often, different machine learning models or statistical, even non-machine learning models make assumptions about the way your data is distributed that might not be true in the real world. How do you do your evaluation and testing? How do you check for bias, robustness, all of those kind of things. And then kind of getting to the title of my talk, in addition to using these kind of scientific principles to understand the results and impacts of systems that we build, I think we're in sort of a new paradigm now where we also need to treat AI models themselves as objects for empirical scientific study. And how do we ask and answer questions like, how do we characterize areas of data or tasks that models do or do not perform well on, right? We have all of these ideas about what GPT-4 can do, but how do we actually test any of them? And, okay, we have this Sparks of AGI paper. We could get into methods discussions about that. Certainly it's only a very first step, if anything. But then we have observations like things like the lottery ticket hypothesis, which is where, we found in some cases, if you have a very large neural network model, once you've trained it for a task, you can actually prune it down to like a very small portion of the original size and maintain the same accuracy as the much larger model. And there are ways in some cases to find these lottery ticket networks that work after pruning, but we don't have a way right now to find them beforehand. Like you still have to train a giant model and then prune it down. But there seems like, right, there should be something, some kind of theory thing there, right? Like, how can we build those more efficient models from the get-go? So, right, how do we start to build more of an actual theory of how machine learning works? And I think that this is a paradigm shift that's going to require a lot of changes in how we think about what results get published and prioritized, what questions get prioritized, what benchmarking and testing infrastructure we use, and all of that stuff. And then I just want to mention a couple other things that I think are important, but slightly less technical, but I think still very, very important for scientific and like technical researchers. So one is using more precision and scientific sort of focused, precise language in how we talk about AI. So this is a paper that we have on a review right now. So like, don't screenshot it. But talking about how the way we talk about AI itself, we often resort to very imprecise, even like magical, mystical language, and how that can be very dangerous. And if we, I think it is useful for us to try to be more precise with how and responsible with how we describe these systems. So even in terms of the results, thinking about things like uncertainty, confidence intervals, again, these traditional scientific approaches to frame your results, but also, right, avoiding this kind of silly mystical language unless you have some real proof that, right, we actually have AGI or we have a theory of mind, like, just kind of claiming superhuman performance, I think is fairly irresponsible. And I also think we should be straightforward about the limitations of models and like when other things could work just as well. Again, something I think we've heard in the previous talks, right? Like, we don't need a transformer for everything. I would argue we probably don't need a transformer for everything. But transformers are very popular. They get lots of money. They're a tool for collecting power if you're the ones who can train them and no one else can. So maybe being more honest about alternatives. And yeah, I think this is related to how the public views science. Like, we already have issues of people mistrusting science and scientists. So if we're just like saying all this ridiculous stuff about AI, like eventually, probably it's going to cause a problem. And then I also think, yeah, we need to always keep in mind the consequences of what we build. So this is one of my favorite papers, again, called Situating Search, which talks about, actually before ChatGPT came out, this idea that language models could replace search. And the paper talks about what role does search serve in society in terms of how we think about the information ecosystem. And maybe it's more useful for you to be presented with, 10 sources that could possibly answer your question, and you have to look at them and evaluate them and learn, rather than just getting, one answer back from ChatGPT, ignoring all the issues about that answer might not even be right or might be not truthful. Like, even just getting one answer back without source attribution, is that really what we want our systems to be doing? And so I think it's always important for scientists to keep in mind, nothing is done in a vacuum. Everything that we do has some kind of consequence. Choosing to propose or accept that AI is a replacement for some kind of function or infrastructure will have a big impact on the world. And I think creating our collective socio-technical future should be something that's like very democratic and participatory, and we can all perhaps play a role in making that the case. And then my last slide, because I haven't been tracking my time and I might be over. I think it's very clear that modern science, by which here I mean post-Enlightenment science, like experiment-driven science, I think it's pretty clear that that is changing or is going to change in the age of AI that we have now. I have this spicy whatever article here, like, are we witnessing the dawn of post-theory science? Like, does theory matter anymore? We can just build a giant model and it makes predictions, and like, what do we need scientists for? And I think that, on some level is a silly question as a scientist, but certainly a question that is being asked, right? And so we need to think about, right, what is the role of science and scientists in the new paradigm of AI? how do we think about concepts like knowledge and theory, and trust and belief in this new situation? And I think a point that I've been discussing with some of my friends that I found really interesting too is, how do we adjust how science is done to match the pace of AI right now, right? Like we were talking about, okay, maybe we want to do more empirical, more rigorous studies of AI, but science papers can take 2 years to publish. By the time you do that, there's 40 new models that have come out. So how do we change it to be maybe a more iterative process or a faster process or things like that, while still keeping some of the tools that are valuable? And I think it's a disservice to ourselves and to everyone else if we don't try to proactively answer these questions. So thank you.
Okay, thanks a lot, Savannah. So I think there's obviously a lot to discuss and think about there, but maybe we'll postpone questions about these topics to the panel that Savannah will be part of later. And we're going to have a break now. We'll have a break for about 15 minutes. So please, help yourself some food outside. It's very nice weather. There's a balcony there that we reserved, so you can go out there, and we'll meet back in 15 minutes with our next speakers, Ahmad. Yeah, she is. I think she said that she was going to be on it, so I assume so. Okay. Hi, everyone. So we're going to start up again. So we have our next speaker. It's Ahmad Tafti. He's from the University of Pittsburgh. And so you can see, if you don't know what that is, you can look outside. So he's the director of the Healthcare Explainable AI, HEX AI laboratory, I guess it is, at Pitt, and many other things. And he's going to talk to us today about explainable AI, what, why, and the next big jump.
Thank you. Hello, everybody, and thank you for coming to this mini workshop. And I thank all organizers to establish this very nice mini workshop for all of us. So my presentation today is about explainable AI. What is explainable AI? Why we should bother with this, and what is the next big jump in explainable AI? Let me show you this. So this work actually is one of the work we have done a few years ago. And when we wanted to do brand classification with the use of artificial intelligence and using plain radiographs. And clinical significance of this work was actually revision for revision surgery. And in summary, I actually provided you with the results of this study. And as you can see, the results of this study was that the deep learning as part of the AI algorithms achieved the same or even higher performance than 2 surgeons in identifying 4 of 4 TKA, total knee arthroplasty implant designs. So the next study I'm going to show you is a study done by Harvard University scientists, in which they want to compare the performance of, again, deep convolutional neural network against some sort of AI techniques or algorithms with surgeons in identifying total hip arthroplasty implant. And the results you can see is actually the convolutional neural network achieved the same or higher performance, than at least one of the surgeons in identifying 8 of 9 total hip arthroplasty implant design. So the next thing I'm going to show you is actually a communication. It was a communication between me and ChatGPT recently. I actually provided ChatGPT with a chunk of clinical text data, in which that text data included some sort of drug names, some sort of implant names, some sort of drug-drug interaction, and things like that. And I asked ChatGPT to provide me the list of drug names in that clinical text data. And you can see the result is actually promising. So indomethacin, naproxen, diclofenac, ibuprofen, they are all available in that chunk of text. So right after that, there was another communication between me and ChatGPT. I was asking ChatGPT when Joe was 10 years old, his sister was half his age, and now Joe is 80. So what is his sister's age? So the question is pretty straightforward and simple, right? For 7 years old kid, for 8 years old kid, but ChatGPT got stuck to provide me with the correct answer. So what I'm trying to tell you with these all 4 examples is this. So do we think, or do we see AI is doing extremely smart kind of things close to one that surgeons can do in identifying total knee or total hip arthroplasty implant, or identifying drug name and drug-drug interaction in a chunk of the text data, or they get stuck, or AI get stuck in identifying whatever kind of, age for a lady in which 7 years old kid can do that. So what we saw is that AI at some point of the time, they extremely start, and sometimes they strongly ignore it, right? They can do whatever our kids can do. So in addition to what Professor Hima mentioned about explainable AI, this is only one way. This is also a way that explainable AI or XAI can come to the table and do something for us, right? To understand why we are getting stuck with some sort of application of AI, why AI gets stuck in solving some sort of problems, and from other side, why we are seeing very promising results, very successful application of AI in different problem settings. So let's start with definition of explainable AI or XAI. So explainable AI actually refers to the set of techniques, strategies, perhaps computational methods to build artificial intelligence systems that are transparent, that are interpretable, and also easy to understand for our end users. So our end users, we all know that they are not mathematicians, they are not health informaticians, they are not statisticians, right? So they could be our end users. They could be physicians without having that much deep knowledge in AI, in deep learning, in rule-based strategies, in those kind of computational methods. So unlike traditional black box type of AI methods, which can be difficult to understand and explain, explainable AI models can design to provide insight into how AI models make decisions, how they can make certain choices, and end of the day, explainable AI is going to help us to understand that AI is not a black box, right? So we can definitely see how AI models can make those kind of decisions and how they can arrive to those decisions. So we still want to go with the definition of explainable AI. So explainable AI has 2 sides. One, we call it explainability. The other one, we call it interpretability. In terms of explainability, for those who are not that much familiar with explainable AI, we can provide a very simple definition saying that rationale behind AI-powered decision-making, we can call it explainability or explainable AI. But if we want to understand meaning of this prediction, meaning of this description with the use of AI-powered models, we can call it interpretability. So the ultimate goal of explainable AI can be divided into 3 different categories. With explainable AI, we can end up with better understanding of AI models. We can also end up with better decision-making. When we see those kind of decision-making strategies with the machine, then we can better understand the strategies, the pipeline, the analysis, in-processing, post-processing, and pre-processing steps. And we can end up with better decision-making. And it could be also more ethical use of artificial intelligence components. So in this slide, I'm gonna provide you with a very straightforward kind of example with healthcare, in healthcare and medical domain. So imagine you are using, or we are using, explainable AI components versus AI components. In AI components, we may end up with the black box nature of AI, in which our physicians or our patients cannot understand what's going on under the hood, versus explainable AI, in which we can provide the diagnostics pipeline using AI to our patients, right? So our patients can clearly understand what's going on in the algorithm. And when we say them, okay, so you will get diabetes with 85% in next 5 years, they will clearly understand what we mean with that probability, what we mean with that time, interval, and all of those stuff. So following about what Professor Hima truly mentioned about the complexity in explainable AI and the level of the accuracy. So I'm going to show you something here. So in this slide, you can see a diagram in which we have y-axis and x-axis. Y-axis represents model explainability, where x-axis explains model accuracy. So as you can see here, so the first thing we can think about that is rule-based model. We are not talking about machine learning model. We are not talking about deep learning model or even statistical learning model, just rule-based model. And to discuss a little bit about rule-based model, I can provide you with an example. Imagine we want to make a mobile application for visually impaired people to help them to distinguish between doors and stairs, right? So this is the door, this is a stair, this is door, this is a stair. So if we look at the stair and we want to come up with a rule-based strategy, mainly from computer vision perspective, if we all look at the stairs from computer vision perspective, we can see each stair does have a list of horizontal lines, right? Versus doors in which we can see many or several vertical lines. So from computer vision perspective or image processing, we can turn the image into grayscale image, and turn it into Fourier transform, do some sort of edge detection algorithm, add all of the horizontal lines together and provide a threshold, saying that if the summation of horizontal lines is bigger than a threshold, then it could be a stair, otherwise it could be door, right? So this kind of method is very straightforward, okay? It's just a set of rules, set of if then else statements somehow, right? But the accuracy is not that much good. So if we look at stairs and define this kind of rule-based strategy, we can see that it's gonna be very similar to the blind, right? So it's gonna be very similar to other kind of, components we may have around us. So if we go a little bit more and deeper, so we all know that with the statistical models, we can achieve better accuracy. But of course, explainability, we will get stuck in terms of explainability, right? Because we don't have that much people know about the statistical learning and statistical analysis. So the story is going to be worse when we go to machine learning strategy, and it's going to be deeper if we go to deep learning models. So deep learning models have already demonstrated very successful applications in a variety of domains, including health informatics, but explainability is still a huge challenge to our community. So moving forward, I would like to highlight some sort of widely used strategies in which we can utilize them to come up with explainable AI. So far we are having three main kind of methods to come up with explainable AI. So one method, we call it example-based, in which we are providing our users, our end users, some sort of examples, example of misclassification, example of true classification, those kind of things. We can also provide them with textual-based information or detailed information in terms of text data or chunk of text data, and also visual-based information. So in this slide, I do have an example for you, mainly in terms of visual-based kind of AI explainability. So in this image, you can see we have had our surgeons utilize eye tracking system, and we gave them some sort of plain radiographs and asked them to identify sigma kind of total knee replacement or total knee arthroplasty implant, right? And what you can see here is actually with the use of eye tracking system, this is the area of the image that a surgeon or a group of surgeons were looking on those areas to identify whether this image or this plain radiograph does have sigma implant or does not have sigma implant, perhaps another sort of implant, right? So, and you can see another results provided by the machine itself, by deep learning strategy. And visually, if you look at these two images, this is one by surgeon, this is by deep learning strategy. you can see that there is a significant correlation between the area that our surgeons will look at those areas to identify TKA implant and the machine itself, right? So in that way, we hope to provide explainability to our surgeons saying that, so the machine also look at the specific, the exact part of the image you guys as a domain expert are looking at that, right? And we always need to keep human in the loop. So let me put it in this way. So one of the philosophy we have in the AI is that with AI, a story is and not or. What I'm trying to say is that what I mean by and is our human expert, our domain expert with AI, not or, right? So in a healthcare community, so we always need to start with domain expert, with our surgeons, with our practitioners, with our nurses, to come up with gold standard data, with gold standard images, with fully annotated images. Without them, we cannot make it, right? And end of the day, we need to have them in the loop to validate the results, to see what we have done with the machine, with the deep learning, with AI, with those kind of buzzwords. So, and with all of that, I would like to finish my presentation with the explainable AI, big jump. What is the big jump and where we are going to go with the explainable AI? So as you will see in this slide, so explainable AI, we hope to get to provide some aims. Like explainable AI, we hope to see more trust to our community, to our AI community, convey confidence in the model to our end users. Again, end users could include patients, could include, physicians, could include surgeons, at least in healthcare community. We hope to get to correlation in terms of capturing correct correlation and association among different variables. We can see in clinical text data, we can see in clinical images, and all of those, various features. We can also hope to get to better, identity in terms of preserve privacy and identity management for our patients, for our healthcare providers. And as all of professors truly mentioned, fairness, right? So mitigating bias towards AI fairness. So be fair and ethically compliant. Reliability is also another big component. With the explainable AI, we hope to get more reliability towards to confidence in AI-powered predictive model or AI-powered descriptive models. With all of that, I thank you so much for your time and being here for us today. And I will be happy to take any question, perhaps now or after in the panel. Thank you so much.
Yeah, we got time maybe for one question.
I've got a pretty basic question. If
Please.
you had a rate on a scale,
Great talk. Thank you very much.
Thank you.
If you had to rate on a scale from 1 to 10, 1 being at the very early 0 adoption stage versus 10 being fully adopted, where do you think healthcare and physicians are on their journey of adoption to AI with regards to that scale?
AI or explainable AI, you are saying? I think you are saying AI.
Exactly.
Yeah, so I have been, thank you, it's a great question. I have been around the health informatics community somehow for many years now. And what I would tell you now, Jamie, is I would say 5 in the middle, because we still have some challenges in terms of implementation science. We are somehow mature in medical image analysis with the use of deep learning models, right? But we are not still in that level to have those deep learning models, precisely in clinical practice. So there is a list of challenges. One big challenge is HIPAA, privacy, security in healthcare community. So, and the other one is, so I have seen also some sort of biases a lot. So biases not in terms of AI, again, in terms of implementation. Let me put it in this way. Imagine, for example, I am using AI components to diagnose something, right? And if I have, let me put it in this way. If I have, I don't know, let's say white patient, right? So I may say, let's look at the AI results, right? With some surgeons. Let's sit together with some surgeons and analyze the results again and again and again. But perhaps if I have a Black patient, I will say, let's do whatever AI is saying. There is still a lot of do together in our community to turn AI into really, really, clinical practice. Yeah, I would say middle. We are still middle of the journey. Thanks. Yeah, thank you. Thank you.
Okay, Jimmy, do you want to? Okay, so our next speaker is Jimmy Grabowicz from University of Massachusetts. And your slides are in PowerPoint, is that it?
Yes, that's correct.
Okay, there it is. Okay, cool.
This is the one.
So
Can
you can, if you want to put it in presenter mode, there's like, you have to be sharing a different. Yeah,
I think
okay,
that's
yeah, perfect. Okay, go ahead.
All right. Thank you. Let me start by thanking the organizers for for making this happen. I think this is a wonderful event and I'm happy to be here. I'll discuss what I perceive as a path towards fair and explainable automated decision-making, but probably this is one of many paths, including research we've conducted with a student I advised, Nick Perello. All right. So I'll discuss this topic in the context of hiring and student admissions. In this context, there are already multiple consequential automated decision-making systems deployed. For instance, multiple corporations outsource hiring to companies such as HireVue, which focus on hiring automation. Also, multiple universities use the Navigate system to predict student success. And one can imagine in the future, similar systems will be used for student admissions. The overarching question that developers and researchers of such systems are facing is how can we prevent such systems from discriminating? To try to answer this question, throughout this presentation, I will show this kind of figures displaying, these are illustrative figures displaying explainability measures. These figures show on the y-axis influence of some group of attributes. Attributes in machine learning, we refer to them typically as features. In statistics, we often call them predictors. So just some kind of input to the model. And I'll be distinguishing between three kinds of attributes: protected attributes such as race and gender, then independent attributes from the protected attributes, uncorrelated attributes, and finally, attributes associated with the protected attributes, potentially correlated with protected attributes. And I'll be always color coding them with red, gray, and blue. They will be also shown in these figures. It will become clear why I'm distinguishing them in a couple of slides. There are multiple ways, as our previous presenter has shown, to implement such explainability measures. Some examples in explainable AI area include SHARP and LIME, so the popular ones, but effect size in regression does similar kind of input influence measurements. To reason about fairness and of automated decision making, we need to consider the entire machine learning pipeline. A supervised learning algorithm, potentially a black box, takes on input a training data and an outputs a learned model. A flow of information is from the top to the bottom here. And the problem of potential propagation discrimination clearly emerges when if training data includes historical discriminatory decisions. The figure at the top shows that the decision-making process generating the training data was directly discriminatory. It was using the protected attribute, which is why the influence of that protected attribute is non-zero on the decisions made. A conventional learning algorithm trained on this data, unaware of this issue, would return a model that perpetuates discrimination. So of course, this is not what we want. An obvious potential solution to this problem would be to drop the protected attribute from the training data so that the model does not use the protected attributes when making decisions. However, this would clearly zero the influence of the protected attributes. The influence of the attributes associated with the protected attributes, correlated with the protected attributes, could potentially change, could increase, as it is shown in this figure. So let us consider these scenarios from the perspective of legal systems. Existing regulation of human decision-making determines that disparate treatment, in other words, intentional discrimination, is illegal, and the usage of protected attributes in the model, one could argue this is intentional. So this would be illegal model. That said, unjustified disparate impact is also illegal. Disparate impact is a correlation between the decisions and protected attributes. Whenever the protected attributes are missing and decision-making exaggerates the influence of one of the associated attributes with the protected attribute, this creates unjustified disparate impact. Examples of this are well known in human decision-making as well. For instance, redlining, which refers to the phenomenon where banks denied services to customers based on zip code, and zip codes are correlated with race. To avoid such disparate impact, learning algorithms can incorporate a fairness constraint requiring independence of outcomes and protected attributes, which is the most studied statistical notion of fairness. This was actually mentioned by Hoda in her first talk. This independence can be achieved in two ways: by reversing the influence of the protected attribute, as it is shown in this figure. So we swap the influence of the protected attribute from the positive one to negative one, or by removing the protected attribute and preventing the use of features that are associated with the protected attributes. So in this case, we don't have the influence of the protected attribute anymore, and the impact of the associated attributes is zero. Now, note that the first technique represents affirmative actions. Affirmative actions explicitly use protected attributes. Unfortunately, recently, Supreme Court is leaning against affirmative actions in student admissions. Furthermore, neither of those two approaches, these techniques, leave space for justified disparate impact, which legal systems permit. So while some of disparate impact are justified, unjustified, and illegal, other kinds of disparate impact can be judged as justified and legal. There are a couple of reasons, typical reasons, due to the relevance. So for instance, in this court case between Ricci and Di Stefano, this is a very well-known court case, tests that were conducted for firemen to be promoted, they were correlated with race, but in the end, they were judged as being relevant to the job and judged legal. But in other cases, they can be justified because they represent voluntary decisions of the affected individual. So in this case, in the case of UC Berkeley admissions in 1973, female students applied to more competitive departments, and so this resulted in lower admission rates for females. In our research, in my research lab, we investigate supervised learning techniques that would prevent unjustified while allowing justified disparate impact. We arrive at a set of methods that we refer to as interventional mixtures. These methods remove the influence of protected attributes, as you can see here. So there's no more influence of the protected attributes, while preserving the influence of the correlated attributes without using them as proxies for the protected attributes, because that would be unjustified. We arrive at a set of a set of methods like this, and let me list the key characteristics of these methods. They are readily applicable to multiple protected attributes. So they address the problem of intersectionality. This is a common issue with fairness notions in machine learning. They are computationally efficient. These are post-processing approaches that function via marginalization of the existing models or optimization. They can be developed for different explainability measures. So I mentioned at the very beginning potential different explainability measures, and they are non-intrusive. If the training data isn't discriminatory, then the method defaults to conventional supervised learning. So it doesn't introduce any new biases than what is in the data set already. So what can be achieved with interventional mixtures? To illustrate this, let me quickly get back to this case of student admissions at UC Berkeley, where females applied to departments with lower admission rates, which resulted in disparate impact. This figure is a graphical model representation showing which variables influence which other variables. In this case, and in general, interventional mixtures allow fine-grained management of influences and associations of protected attributes. They remove the unjustified relation, the justified impact of the protected attribute on the decisions, while preserving the justified influence, so the influence of the department on the outcomes, while also preventing unjustified change in the influence of the correlated attributes, so in the change in the influence of the choice of the department. These operations can be performed with respect to other attributes as well. So, for instance, SAT scores and essay scores, they are shown to be also correlated with protected attributes, and interventional mixtures can correct them by removing any relationships between variables that are judged as unjustified. Of course, this raises a big crucial question, which is who should determine whether a given relationship is justified or unjustified. I believe such process should be involving stakeholders and domain experts. In the case, they judged all relations of the protected attributes as unjustified, then interventional mixtures would remove all disparate impacts. So through this process of model development, explanations, research, there still is a way towards achieving affirmative actions. So this is just what I said. And this is taking me to a broader vision that I have of a registry of consequential decision-making models in the form of input-influence attributions, where in my view, the goal of such a registry should be to incentivize growth towards a fairer decision-making rather than penalizing existing decision-makers. This could be achieved by making comparisons among models for a given type of decisions and targeted audits. That would also facilitate convergence of research by aggregating and systematizing models of human and machine decision makers. And finally, that would foster, of course, trust in decision-making processes themselves, as Ahmed mentioned in his previous talk. Explainative measures can be applied to output of large language models to explain their own decisions. And this is my last slide. So thank you very much, and let me know if you have any questions.
Well, thank you. So yeah, we definitely got time for a question. Is there one online or anyone's got it? Okay. Online. Sure, go ahead.
Yeah, sure. So somebody on is working online asked, there have been some recent discussions between the president and CEOs of AI companies. How could better informing their policy decision-making have an effect relative to your work?
Could you say the second part again?
Yeah, so they asked, how could better informed policy decision-making be affected by this?
Yeah. This is a great question. There is NTA's request for comments, and we do want to respond to that request. I do. I mean, this is of course just my belief, but and of course these are very challenging problems to tackle, and the issue of developing a policy is an enormous one. It's just that the breadth is huge. But I think I think we want to move towards more transparency as a society, and that can potentially both help our own decision-making processes and, of course, machine decision-making processes to become more accountable and more fair. So this is the way I hope things will develop. Thank you.
So Przemek is on the panel later as well, so we can follow up on that. So the next speaker is someone who's online. So it should be Catherine Stange, sorry. And she's going to talk about, can AI be used to prove mathematical theorems? And let's see, so I should stop the screen share from here. Okay. She's not shown up. Okay. All right. So we can move on to the next talk in that case if she's not. Is she on? Oh, okay. She should be on the list of people. Stange, yeah. So yeah, sorry, Catherine. So yeah, we're just going to make sure you have access. So when you're ready, you can share your screen.
Aha, there we are. Thank you for
Yeah, we got you.
permissions
Okay.
there. Okay, share screen. All right, do you see my slides now?
Yep, we do. Yep. Can large language models prove theorems? So
Okay,
yep, so
great.
you
Thank
can
you.
just go ahead. Yep. Thanks.
Thanks. Okay, so thank you very much for the opportunity here. So this is not a scientific talk, it's a bit lighter. I'm going to describe some of my pretty modest experience with the large language models as a mathematician. And it's sort of just in the spirit of sharing experience across the many disciplines that are represented here. So my question is whether these large language models could eventually become mathematicians, or maybe just aids to mathematical research. So that is, can they think mathematically or prove theorems? Sorry, I've got too many. There we go. Okay. And so first, I'd like to tell you about a student who is passing my discrete mathematics course. So this is a course which introduces proof to our math majors. And the student doesn't do perfectly, but they're an A- student at least. The mistakes that they make are often the same common student mistakes that I see on a daily basis. Like other students that I do tend to think highly of, they sometimes make the sort of unimportant algebra and arithmetic errors that we all make, but still keeping their eye on the goal and using the correct overall proof structure. And in fact, I'd like to encourage them to continue in mathematics. Although, come to think of it, they sometimes over-optimistically try to shoehorn a favorite example into a place that it doesn't fit, sometimes sort of willfully ignoring the signs of a contradiction. And I try to teach my students to know what they know and know what they don't know. And this student seems a little too confident in their incorrect answers, but again, that's not uncommon in students. Also, I must admit that they sometimes lack creativity. So their beautiful formalism, which is really a balm to the heart of a teacher of induction, sometimes surrounds this sort of dissonant nonsense that they're using to attempt to bridge a gap by brute force, where maybe something more subtle is actually needed. So in these situations, when they make a mistake, they sometimes do so with such sort of stunning disregard for basic algebra or logic that I can't even square it with the previous impression that I might have of them as a diligent and careful thinker who is scoring perfectly on negating sentences with quantifiers. So the student is just a little bit mysterious, and come to think of it, suspiciously obsequious, always apologizing politely at the least hint that they've made an error, apologizing politely and contritely before shamelessly and with complete confidence asserting another completely erroneous solution in a tone stolen from a textbook, as if they're lecturing me. Sometimes during office hour discussions, I do have a hard time preserving my composure. But fortunately, the student is only auditing my course. They rarely attend lectures, but they show up for exams, having obviously studied the material off the internet. They occasionally use unfamiliar terminology, for example, but I don't mind because I find the student fascinating, and the student is, you might have guessed it, ChatGPT. So I am a number theorist by training, and the only way that I can really currently evaluate ChatGPT, and I'm mostly talking about ChatGPT 4 here, is by comparison with my students and colleagues. So this is by no means a scientific talk or a scientific study. There's a really fascinating study by Frieder et al. Called Mathematical Capabilities of ChatGPT, and it largely matches my experience. And my purpose here is just to describe my personal experience and my guesses for where we might be going in the future. So big observations on what ChatGPT 4 and Bing and Bard seem to be able to do. If they were a human, what I would say they are capable of. So it certainly seems that they understand form and formalism. So ChatGPT can write a beautifully organized argument with nested layers. They do seem to be able to manipulate concepts based on prior knowledge. So when they're faced with a known concept in a new situation, they can bring up important relevant theorems and use them the right way, or recognize a definition from the concept without the name. They can manipulate new concepts based on novel mathematical definitions. So this is quite impressive. You can give ChatGPT a new definition, and it can give correct examples and even suggest possible theorems, small theorems, and prove those. So the generated content can actually be novel. So sometimes I see things that are not just thinly modified versions of things that already exist on the internet or that you may have already suggested to it, but apparently new logical combinations of concepts put together in some way that has not been done before. On the other hand, it seems to be missing a few things. So in my experience, one of the things that is missing is self-monitoring or cognitive self-regulation. So it doesn't seem the least bit bothered by or even be watching for contradictions when it's giving a logical argument. When we're going through a logical argument in our heads or explaining something to somebody, we're usually following little side paths as we go, and maybe we see a warning sign in one of those and it makes us stop mid-sentence and say, hang on, I just realized this can't be true because, and it doesn't seem to do any of that. So it makes it seem as if it's very not self-aware. Logic. So I just said all the things that it can do, but actually it seems to really lack logic, especially in the situation where it doesn't have context. So if it has context, if it knows what conclusion you're expecting it to reach, it will usually make a plausible logical inference. But for example, if you ask it to, so that's, the example I was thinking of there was like the standard sorts of proofs that you ask in a course on a first course on proofs, maybe proof by contradiction or proof by induction. But one of the first proofs that I give my students in such a course is a 3x3 Sudoku, and just prove that you can or can't solve this Sudoku. And ChatGPT 4 just, it cannot do this even with multiple attempts. It ends up mixing up the rows and columns or just outright breaking the constraints and putting two 2s next to each other. It seems to sort of lose the ability to know where it's going when it has to really rely on pure logic instead of contextual clues. So in that way, it sometimes kind of reminds me of when you're having a dream. Maybe it's like a dreamer who, the alarm goes off and the sound intrudes on your dream, and then your dream kind of backfills some explanation for why there's a sound there. And I feel like ChatGPT is doing a little bit something like that. It usually knows what conclusion you wish to reach, and then it sort of gets there one way or another. Another thing that I've noticed is that, it knows a certain amount of math to a certain level. So I'm assuming it's been trained on what's available on the internet and textbooks and materials from course websites and so on. And so it seems to be able to learn what we've sort of canonized at the college level in mathematics. It can absorb standard material, but this is material for which there are thousands of examples because this course is taught at all of the colleges around the US and around the world. And it doesn't seem to have any realistic grasp on research level math. And it's not that that's not in the training set, because for example, if I ask it about one of my research topics, it can give me the big idea. It can tell me a little bit about what the research topic is for or about, but it can't say anything that is simultaneously really reliable and precise if you push it on anything. And I think maybe this is because expertise in that area means reading a lot between the lines. It's not just some sort of statistical, familiarity with many examples of something. And next, I would say that it is not seeking truth with humility, which is what we're looking for, right? I would say it seeks plausibility with great confidence. And so this is connected to the last thing. ChatGPT 4, as you know, if you've interacted with it, is a compulsive liar. So you press it on anything and it will, rather than saying it's not known, it will invent theorems and it will give you bibliographic references. These have page numbers and everything, plausible sounding titles, and in fact, real authors whose work is in the right general research area, but the papers don't exist. They were never written. And this reminds me of a quote from a researcher at Google, that BARD and ChatGPT, these are large language models. They're not knowledge models. Okay, so can it prove theorems? So some conclusions and some conjectures. So first of all these drawbacks, most of them to me seem to be sort of a matter of degree. So not kind of some intrinsic barrier. So maybe adding, teaching it to add a layer of self-reflection, it can learn to recognize its own contradictions and watch out for that. But I do think that that the reliance on the training set, the sort of question of whether it can go beyond its training set, is maybe an intrinsic barrier. So it seems, just 1 second. Sorry, I keep losing my window here. So it seems like it can reason about novel mathematical definitions, but the examples that I've seen that happen with are modifications and combinations of ideas that it is well versed with through the introductory courses. So even though the definition might be new, it's still about or built upon one step further from things that it seems to know well. So it might be that the best it could be is really a repository of human understanding and not really a source of new understanding. I find it kind of interesting here to compare to large language models, to compare these large language models with image generators. So do we expect image generators to be able to develop whole new artistic ideas, or do we expect them to forever embody those artistic ideas that have already been invented? All right. So can it help us discover new mathematics? So I think almost certainly it'll eventually be useful. So right now the lies and the illogic are just too frustrating. I'm not actually using it in my research. But as a new way to access the collected wisdom of centuries of mathematicians, I think it might eventually take its place. It might be able to do things like find all of the places that a mathematical idea occurs in different subfields. So rediscovery is a common occurrence in math research right now. It might know the accepted strategy for a whole class of proofs that maybe I haven't studied in my own area, but suddenly need for my research. It might know the established names for some concept that I've come across, but I don't know the name of. It might be able to help search for prior results relating to something like an equation, which Google can't do very well right now. So I think it might end up sort of taking a place alongside Google and Math Overflow, for those in the know. But this raises a question, which is how will we cite it? We've historically been very careful as mathematicians to trace the genesis of ideas, and this will make it very challenging unless the AI can learn to cite its own sources. And so I'll end with a question, which is, do these observations reverberate in other natural sciences? So I'd love to hear from some of you, and thank you.
Okay, thanks a lot, Catherine. That was fascinating. So yeah, we'll definitely be discussing these things in the panel. And if you're around later for the panel, we welcome your input as well. I don't know if maybe do we have time for one question? Maybe one question, I know, from the audience here, or do you want to save it for the panel? Okay, so I should just point out Catherine right now is in the lead in the AI versus human contest. She doesn't know. But yeah, so if you can beat 39 out of 54, that's the current high score. You've got until 4 p.m. So, okay, thanks a lot, Catherine. So we'll hear from you later. We'll move on to the next talk. Okay. Okay, so the next speaker is Stephanos Christian okay, sorry, I can't pronounce your name. I haven't memorized it. Yeah, so Stephanos Christian Rolmasira from the Education University of Hong Kong and Satya Wakana Christian University, and I think he's in the Indonesian time zone. And so I don't know what time it is there, but are you there, Stephanos? Okay, cool. All right, so Stephanos, you can share your screen. So he's going to be talking about developing AI literacy for the next generation of scientists. Okay, cool. Yeah, we can see you. So yeah, you can. Screen now and hide that. Yeah, you can go ahead.
Okay, can you see my screen now?
Yeah, we can see you and your screen. Yep, you can go ahead.
Okay, all right. Okay, thank you for the opportunity given to me, and yeah, good morning, everyone, and good afternoon. Right now, I'm presenting remotely from Indonesia, and it's now 2:15 a.m. and I'm glad I'm still awake. Okay, so first of all, I would like to express my gratitude to the Committee of Responsible AI workshop for allowing me to share this ongoing research regarding AI literacy for children in Indonesia. So I'm a PhD student at the Education University of Hong Kong, and I'm also a lecturer at the Faculty of Education at Satya Wacana Christian University in Indonesia. And I would like to take this opportunity to share my presentation, my research paper. Actually, it's part of research paper that I worked with Dr. Yu Chi Lai from the Education University of Hong Kong and Dr. Jonan Philip Donaldson from Texas A&M University. And in this presentation, I will talk about developing AI literacy for the next generation of scientists. So I will start first by explaining why AI literacy. First, it goes without saying that AI technology is improving rapidly as many researchers and companies utilize AI technologies to improve effectiveness and efficiency of their work. So in the future, scientists will be able to use AI to help them analyze vast amounts of data more quickly and accurately than ever before. And more importantly, they will use AI in ways that we can't imagine today. So therefore, there's an urgent need to prepare our children as the future scientists to work in the situation where AI is ubiquitous. And secondly, why AI literacy? The work of future scientists will be impacted by AI. Well, for example, they can use AI in the experiments and simulations, helping scientists to test their hypothesis and predict outcome more accurately. So this will not only increase the efficiency of scientific research, but also allow scientists to tackle more complex problems and make more accurate predictions about the future. And the third reason is that future scientists will not just require to be able to use AI, but also collaborate with AI to solve more complex problems and make new discoveries. And the last reasons why AI literacy is future scientists will face many ethical issues regarding the use of AI. They need to be aware of the issues related to biases, safety, privacy, intellectual property, and any possible negative consequences that it may cause. So therefore, we conducted our integrative review related to AI literacy to finding out the existing framework of AI literacy, and we make a conclusion based on the existing framework of AI literacy. And the conclusion is there are 4 core constructs of AI literacy. So first, recognition of AI, then explanation and evaluation of AI, interactions with AI, and the last one is ethics in using AI or collaborate with AI. And in our research, we use design-based research to give intervention on how to help the kids learning AI, develop their AI literacy. So in the context of children in Central Java province of Indonesia. So we conducted the research in 3 elementary schools, and in each intervention, there are 3 sessions, consists of 2 hours in each session. And in the intervention, we include unplugged activities. And as an example, students were working on categorizing jumbled pictures into their own categories and then explain to their classmates about how they come to the conclusion. And with the hope that students will learn about the concept of machine learning. This activity can help students to understand the concept of data training in AI. So by demonstrating how data is organized and labeled to train a machine learning algorithm. So the process of categorizing the pictures is similar to how human label and organize data to help training machine learning models. Then after that, students were learning about using AI. They have hands-on experience in this case with AI by using teachable machines. And so it can help them to understand how data is used to train machine learning models and how these models can be applied in various real-world scenarios. And then as an interactive part in AI literacy learning, students, they collaborate with AI in arts. Students in this case working together with AI to make a piece of drawing according to their own imagination. The AI tool that they use in this case is AutoDraw. And each student starts by sketching a basic shape or outlining using AutoDraw, and then pass the drawing to their teammates to add their own touches using AutoDraw. This process could continue in cycle until each team member had a chance to contribute to the drawing. So by working together in this way, students can learn how to collaborate effectively with both their peers and AI, and develop their creativity and problem-solving skills. And they can also learn how to adapt and build on ideas of others, which is, I think it's important skill in many areas, including art and technology. The data that we collected were students' written reflections about what worked, the struggles that they experience or they have, and the experiences, the learning experiences in each meeting. And then we coded the data and conducting cluster analysis to help us create the design moves. And you can see that this is the network map based on the students' reflection, that we generated this network map by using Girvan-Newman cluster analysis. And if you look at the sizes of the nodes, it reflects the betweenness centrality values. And each cluster represents a set of interdependencies of things that work well, the struggles that the students experience, and alignment of experiences with theory principles that we can use to tackle the problems students have in the learning activities. So we are using relationships between the struggles, what worked, and principles from the theory in our analysis. And then we leverage strengths and theory to address the struggles. And finally, we created 10 design moves. And actually, what I mean by design moves is actually the things that we will change about the learning experience for the next iteration. So based on the findings, kids in Indonesian elementary school, they can develop AI literacy quickly, and they were very excited, deeply engaged, and these future scientists, I could say, they are eager to embrace AI, but also surprisingly thoughtful about positive and negative potential impacts. And our research suggests that developing AI literacy for elementary school students requires generativity when students involved in learning activities that allow them to make something. And then collaboration, where students work together to build their schema of knowledge about AI. And only after generative and collaborative engagement, students will be prepared to evaluate the impact, the uses, and ethics in AI. So we believe that there is an urgent need to cultivate AI literacy for the next generation of scientists, as AI will significantly impact the future of science and making scientific methods, ways of knowing, and paradigms inseparable from AI. So therefore, in our last slide, this is as recommendations. These are the call to action that educators at all levels must prioritize AI literacy development and integrate AI literacy into curriculum in all science courses. Thank you.
One question, if there is one. Is there one online or not? No. Okay. I guess time is a bit short anyway. So, okay, thanks a lot. So yeah, we won't keep you up any longer. Thanks that you stayed up. That was great. Thanks. So we're going to move on. The next speaker is, let's see, I have to look, should be online also. It's Soo-Kyung Kim from the Palo Alto Research Center. So I know, is Soo-Kyung Kim online yet? Okay, so yeah, Soo-Kyung Kim. So she'll be talking about towards physically reliable molecular representation learning. And all right. Okay, maybe I'll let you do the full screen. Okay, so Soo-Kyung, we're just getting your on the screen. There we go.
Can you hear us now?
Hi,
Great, we can hear you.
can you hear me?
Yeah, we can. Yep. Loud and
So,
clear.
she's coming right back.
Can you hear me?
Yes, can you hear us?
Okay, seems like
Okay, well, it's her problem, not us, because everyone else is working.
Okay.
We'll figure this out.
so yeah. Not sure whether you guys hear me.
Can you chat and just tell her, tell her to go ahead, we can hear.
Great. So let me share the screen. Yes, I can hear you. So yeah, I will start.
Yeah, go ahead.
Yep. Yeah. Right. So my name is Sugyung Kim, and I'm from Palo Alto Research Center. Today, I will talk about my recent paper I just accepted from UAI yesterday, named the Physics Empowered Molecular Representation Learning, and I'm collaborating together with Seoul National University. Okay, so predicting energetic property in molecules is very, very critical task in material design. So there are many neural net-based models out there to predict the energy given the sequence of the composition of atom and its positions. So basically, the modules consist of the graph neural network or transformer, accept the location information and atomic representation as the input. And as the output, it predicts the energetic property like total energy and HOMO-LUMO gap and so on. But there are many models out there working really great to predict the energy at a stable state. But the problem is it is not enough to estimate the full potential energy surface. What it is most models are trained at the most stable structure, which is the minimum energy. So it is doing really great job to predict the stable energy. But it's not predicting the energy at non-stable state, which means that non-minimum energy structure surface. The problem is that because of that, if we take that pre-trained existing neural net-based energy estimator and try to relax or optimize the molecular structure using that neural net-based energy estimator, it gives us a really, really long, physically wrong result. So because it just trained with the stable energy state and cannot predict the energy at unstable state, if we use that model in molecular relaxation task, then it ended up to very unphysical result because of the very unphysical potential energy surface. So for example, let's see like few of state-of-the-art model like SCHINET, FirstNet, DimeNet, MXMNet. Those things are all different variable of predicting total energy given molecular structure. So this is the optimal structure, ground truth. So we perturb a little bit of the structure and try to relax or optimize the atom using the energy predicted from those neural net estimator. You can see that it ended up to really unphysical structure, like those atoms are falling off from the main structure, and those structure are really look differently with compared with the ground truth structure. So our model is basically the main idea of our model is just to stay the same as existing skeleton of the neural net architecture, and then we induce the physics-based constraint on the top of that. So I will just explain the structure of our model in a nutshell. So basically, our skeleton is consisted of the transformer structure. So this is the example of CH4. So in CH4 structure, we tokenize each atom as the vector called X, and this X contains the atomic information, such as like this atom is hydrogen, and hydrogen has some specific property and blah, blah, blah. And then also the nearby neighborhood information around that specific hydrogen. So this X contains the information of this hydrogen and the surrounding neighborhood around this specific atom. Then after we tokenize it, we plug it in as the token of the transformer. So there are multiple molecular attention block. And in this molecular attention block, we fed this adjacent matrix A as the additional input. just to learn the 3D geometry of the molecule. And inside of this attention block, in addition to query and key, we give the additional information called D. D is basically one atom to another atom's distance. So in that way, this transformer learned the better representation of the 3D structure of molecule. So once we get the output from this transformer, we sum them up and then train the regression error of the total energy. So this transformer is basically neural net-based regressor to compute the total energy of the molecule. Okay, so far so good. So this structure is basically, we borrow the structure skeleton from the model called DimeNet, one of the state-of-the-art energy predictors. So in addition to that, we induce the physics-based constraint. First of all, rather than just using total energy, we split the total energy as a self-energy and bond energy. And self-energy is just the transformer predicted total energy, and this bond energy is basically again split by as the summation between Coulomb energy and Lennard-Jones potential. And as the analytical form of the Coulomb potential and Lennard-Jones potential can be written like this. We just predict the subparameter to consist this equation of Coulomb potential and Lennard-Jones potential from the representation we learned from the last layer of the transformer. So just get rid of the last layer of the transformer, and then from the embedding of each head of the transformer, we predicted each parameter that can be plugged into Coulomb potential and Lennard-Jones potential. And this F bond is basically MLP. And then in order to make this model guide the molecular structure to more stable structure, like guide gradually to the stable structure, we induced the two more physical constraints. First of all, zero force regularization. So when the molecular structure becomes stable, net force will be zero. So this is, for example, the stable structure energy point. Because it's like this shape, like this concave shape, at this point, the derivative of the energy would be zero. So to guide the structure to become the net force equal zero, we added the force laws, such as the derivative of the energy for X, Y, and Z direction, and sum them up, and then added to the laws as the force regularization laws. And also inequality bound condition. Inequality bound condition is nothing but locally perturbed molecule must have the higher energy than the unperturbed one. So for example, if we perturb the molecule and from the stable state, then it will become unstable state. So the energy should be higher. So if that is not true, we give the penalty. So for example, if the perturbed energy is actually lower than the stable structure, then that's wrong. So we give the penalty. Okay. And the most important regularization is the masked atomic modeling. So inspired by the masked language modeling from NLP, we did the similar things. Basically, given the token as the input, we took portion of the token and masked them out and let the transformer predict which atom would be at this masked location. So by doing that, we can learn better representation of the molecule. So as we can see, this is CH4. If we move this C up and down, this is the class prediction result for this empty seat. So answer is carbon. But if we move this atom up and down, the prediction accuracy as the carbon will be decreased, which is obvious. Sorry. So our result shows that our model is not doing as good as energy predictor for the other models for predicting energies, but when we predict the force and when we use that model to relax the structure, it will have a better performance. So the main takeaway of our work is, even if the previous model to predict the energy is really doing great job to predict the energy, that is only because it is fine-tuned to the stable structure. So we cannot use that model, like pre-existing model, to relax the structure, like in practice, because it just predicts the stable energy correctly, but that predict the force or the structure outside of the stable region. But our model performed really great at prediction accuracy of the structure. So this is a qualitative result, like or other model starting from the ground truth and the perturbed structure ended up to wrong structure if we use those model as the energy predictor. But if we use our energy predictor as energy relaxation module, we will get the very, very similar, almost same as the answer as our final structure. So the main lesson for this is it is very important to consider the validity of the potential energy surface, not just the energy, because we want to use that energy module in practice to relax the structure and then design a molecule. And also physical constraint dramatically improve the efficiency and accuracy of the proposed model, because by doing that, we can extrapolate the structure relaxation even outside of the training data scope. And Bertha-style masked atomic module is very helpful to learn the better representation of the molecule. Okay, thank you.
Oh, thank you very much, Soo-Kyung. So again, we have time for maybe a question. Is there one online? Okay, so yeah, I guess it's good. Okay, speaking as a physicist, it's good to see physical constraints actually used to improve the model. So that's very nice. Hopefully, we can think about how we can apply that to other areas of AI that we've talked about. So, okay, thank you very much for your talk. Okay, so we've got in the schedule, we're running a little bit behind, but that's okay because the next talk is going to be at 4 p.m. It's going to be Stein Sigurdsson, I think. Yeah, that's it. And so at 4 p.m. also, we're going to close the AI versus human competition. So if you haven't tried the discriminator phase, you can go ahead. You can find the link on the conference webpage. All the examples were submitted by conference participants in the generator phase. And right now, as I said, Catherine Stange, the speaker we had before, is in the lead. But I think we're going to give prizes to the top 3. And if we can figure out how to announce who's doing the best, maybe shortly before the panel, we can do that. So anyway, if you've done it, you can think of it as a break. Again, there's tons of food. You need to eat at least 5 bags of chips each. And I will see you at 4 p.m. Okay. The last talk of the afternoon. We've got a panel after, but the last talk we've got Stein Sigurdsson. So he's from Penn State University. He's an astrophysicist, but also the scientific director of arXiv, the preprint archive. And he's going to talk about the end of science.
Well, somewhere in between at least. So I'm talking here with my arXiv hat on, not literally, but good afternoon for those of you still hanging on out there in the interweb. So first of all, given the composition that we were sent about the audience, I'm going to do a little quick background on what arXiv is, although I expect at least half of you are familiar and probably frequent users of it. arXiv is a preprint service. It's the original one, going back to 1991. It's a open curated research sharing platform, free to read and free to submit, covering mostly physics, math, computer science, and some other categories of science and academia, but their core audience is the physics, astronomy, mathematics, computer science, statistics. This is where it started. I still have those. This is a primary motivator for developing this thing. Archive, just so people get a sense of its scale. And by the way, if those of you who don't know, it relocated to Cornell Tech from Cornell. So Archive is now headquartered in New York City. We do 15,000 papers plus per month. We are going to hit 200,000 this year, new ones. We are already well over 2 million papers. It's fast. We do 5 million downloads per day. It is very thinly staffed. We have 15 people, at least 4 of whom are part-time. And then we have advisory boards, 25, 30 members, fluctuates a bit, and about 200 moderators covering about 150 categories of science. Okay. So leave this up here for a second. Everything in the world that is of interest is explained by an XKCD cartoon, either a current one or one in the near future. We rely on that. Those of you who are aficionados know you can have an entire conversation just saying XKCD numbers and giggling. So don't jinx it. Growth is pseudo-exponential. Our mathematician colleagues insist that it's not actually exponential. The weird structure in the top corner is COVID. We're seeing us emerge from COVID. And we think we're going to resume a fairly steady trend of pseudo-exponential growth. Okay, so how does Archive fit in with AI and responsible uses thereof? So first, a confession. We use AI. We are AI users. We are proud. Some of our AI is obvious. Some of our AI is not obvious. Some people are quite surprised when they hear we do stuff. But for example, we have a weak AI for text anomaly detection and trying to parse unprofessional content. That'll also, you should then realize we're doing text extraction. In fact, Archive, one of Archive's criteria for submission is that all papers must have a source that is suitable for extraction for natural language processing. And this is provided. It's on Kaggle, it's on Amazon, Glacier things. It's a couple of dozen Samizdat copies around the world. We know they're there and don't do anything bad with them. And it's a core piece of most LLM training. If you look at the training sets, Archive is a hefty chunk of the cleaner data they use. We also run an internal classification system. We have a static, inline, fast parser. It's an OMFIT variant, which does synchronous category recommendation for authors. Then we also have a dynamic in the sense that it is sort of partially updated as it goes along. It takes in data, it doesn't use fixed syntax. But it's run asynchronously on the full text. We run it asynchronously on the full text for various reasons, one of which is that it's not fast enough yet to do it on the fly. And it does also category testing, and we also compare that. And yes, there are serious responsibility issues on that, and a lot of people get very agitated when they hear this because there are in many ways that's going to introduce bias and lead to adverse outcomes for authors, but we have to. Most of our AI content is through the formal collaboration for something called Archive Labs, which most people, by the way, doesn't know exist. It's at the bottom of the abstracts if you go and look at them. It's about a dozen different collaborators currently. We are always soliciting new partners. Papers to Code is in there. Hugging Face and Replicate AI are both relatively recent collaborators. We have recommendation engines and knowledge graphs. The most recent one that we brought on board 4 months ago does AI-generated audio summaries which is using LLMs to parse papers and provide audio summaries, partly so you can listen to it on your bike ride and partly so for accessibility. That's actually one of our pathways into improving our accessibility. And we'd like to do more if somebody gives more people and more money. How do we get people and money? Okay, so let's talk about language tools. Does anybody know about SciGen? No old MIT grads anywhere? SciGen was a hack by a couple of MIT students in 2005. And they used a context-free grammar model to generate spoof papers for computer science conferences, and then submitted them to them and got them accepted. Very shortly afterwards, Paul Ginspark had developed a tool to detect and reject SciGen papers, and we still get them. There's still MIT undergrads that discover this tool, and think they're being funny. Fast forward to modern times. On the 30th of November, ChatGPT-3 was announced. We do keep an eye on these things. Also, they all come through us, so it's fairly easy. I can see all the OpenAI papers before anyone else does. So on the 3rd of December, 30th was a Sunday, there was a Slack message sent to archive staff. And on the 31st of January, after some very hasty coordination with other archives and journals, informal coordination, and with our advisory boards, we announced a ad hoc policy on use of AI tools. We're trying to be very responsible here. The policy is on our blog if you want to read it. Nobody ever reads our blog. It's very short and simple. It requires, well, it bans AI tools from being listed as an author. Right now, if you list a ChatGPT or something as your co-author, we gently tell you, no, don't do that. And you get sent back. At some point, it'll probably lead to, don't try that again, or you'll be in trouble. We are currently requiring and requesting authors to report relevant use of software tools in accordance with the scientific standards of their respective subfield. So if computers and society say, oh, heck with it, everybody just go wild, the chatbots will go, okay, that's really what you want. Go for it. Or otherwise, you're expected to say in the acknowledgements or in section or somehow, whatever your favorite way of referencing to things. We use ChatGPT for this. Crucially, on submission, all the authors jointly take responsibility for the content of the paper. So if you ran ChatGPT-3 through it and it hallucinated, or you had Galactica spit out a bunch of fake sites, you own it. Not going to get to blame the LLMs. And if such things are spotted and reported to us, we take whatever appropriate action is called for, given the context and standards of that subject area. This is the slide that I edited and forgot to delete. All right. There we go, our Slack channel. I assumed everybody already has seen the ChatGPT announcement, and I was like, okay, it's going to cause problems for us and all of academia, sorry, pronunciation, potentially in an interesting way. And A, we have to start strategizing on this, and B, can we get some money? And then December 8th, we had our first fully ChatGPT-3 generated submission, which was promptly rejected. If they don't do that again. By the way, if you're gonna, well, back in those old days, if you're gonna do stuff like that, don't announce it on Twitter. We do keep an eye on things. All right. Now, here we go. Right now, we have 415 articles that in some way mention ChatGPT. That includes the ChatGPT trying to do math paper. It includes Microsoft's, oh my God, it's AGI. It includes the full 100-page technical report. And this is a tiny fraction of all the different LLM research in there. A little bit of advertising here. The speed of all of this happening, which was mentioned earlier, that's archive. The big part of the turnaround in this area in particular, and by the way, machine learning is now the single largest category in archive and still growing insanely. The moderators of that area are doing an absolutely heroic work because they turn around almost all those papers in less than 27 hours. Several hundred per week. Where was I on this? Yeah, so if you had to wait for the stuff to come out on a journal or even a conference, you know, it's not going to come out till like the third conference to submit to. You'd be waiting a year and a half to actually find out the details of what's going on inside. We routinely have papers come out on Thursday. People think about them over the weekend, and on Monday the rebuttal or the follow-up is there. Astronomy is really good at that. It's like data interpretation, wrong. Or my model is much more better. That's also a responsibility in science. Okay, so is this actually really something unique? You know, are we going to have war against war of all against AI in the near future? I never really got the Butlerian jihad and how they won it, but I gave up reading Dune before I got to that bit. We've had qualitative transformations both in doing science and producing science. There have been several such. They're all pretty major, actually. I'm old enough to remember calculators. Those are the things, the little overpriced iPhone app things that they sell for $100 to high schools. You know how much the chips in that Texas, whatever it is, actually cost? They're using 8080s. There's a factory in Arizona that makes them for 1 penny a chip. Yeah, it's insane. Calculators were transformative in doing simple math. It took away the drudge. Like 2 of you at most have ever used log tables. But you know what? They're still restricted. Even down to their exams, there's the calculator section and the not calculator section. And you have to power off your watch. It's going to fail this summer when you're going to have to power off your glasses. The rumors are true about what's coming out this summer. And if you're feeling generous, ChatGPT is just sort of a slightly OP Clippy. And that's just annoying. And the number of times my iPhone tries to predict what I'm actually going to write, and I'm actually trying to say something in my native language, and it doesn't notice that I hot keyboards. It's horrible, and sometimes I have to apologize. I also find the habit of certain word text producing documents of trying to complete my sentences or suggest what I really want to say to be counterproductive. So, you know, maybe LLMs are just grammarly on steroids, or, you know, clippy vampires. On the other side, there are the symbolic manipulation programs. For example, Wolfram's Alpha, Descender Mathematica. Serious math is being done on those. And it is a massive productivity enhancer for people doing actual calculations, at least, real grown-up calculations. And if we had to do them again by hand, there'd be a lot fewer papers in certain fields of our science. So is LLM really another qualitative transformation? I mean, right now we really are just at the prototype stage. I know they've been growing, and but they're not done, I don't think. Or maybe that's wrong. Maybe progress is going to slow down or plateau this summer. I don't think so, but it could happen. From my perspective, they're getting better fast, and we're training them. When you play with ChatGPT, you are training it. You're providing human feedback, and it's sucking up your brain for the greater good. I actually have 3 tabs open on my laptop right now. One for my ChatGPT 4 access, a 3.5 plus, whatever they call it, and then the original 3, which has been open since 1st of December. And I play with it quite a lot. It's fun. It's a good conversationalist in some ways. It's sometimes a bit silly, but you know, so is my dog. But I still like it. They hallucinate. They lie. They try to please you. They're great. It's like having a slightly drunk friend who knows random stuff and spouts it out after 3 beers. But I don't know if you've been following what's I think being referred to as the Cambrian explosion. These things are getting better really fast. And there's a lot of really, really clever people who are finding ways to jailbreak them, gently leak the weights to the hacker community, put them in wrappers, install guardrails. There's a huge effort in the scientific community to do physically constrained modeling. Try to force it to put in conserved quantities or have logical constraints on top of their free association texting. And it may yet kill us all. Have people seen Chaos GPT? Somebody just for lulz did a launch a GPT, and the prompt is find a way to kill all of humanity and start working towards it. Go. I don't think it's quite good enough yet, but it's probably listening to me. So, all right. So where are we with the AI in science right now? And what should we be doing? What should we not be doing? AIs are generally a productivity tool right now. They take the tedium out of some things. They do stuff you couldn't do really on a realistic timescale without them. This is like where they're basically doing a huge principal component analysis or some toy thing on a very large data set. But they're also a massive junk generator. And in particular, where we are, everybody's already drowning in data. There are way too many papers on way too many subjects. People can't keep up anymore. We need ways to reduce the data and summarize it, not flood us with more. And it's very, very easy to generate complete and utter crap that sounds really plausible and a good read with a ChatGPT. And it's happening. There are people who are churning out already pseudo papers. They sort of make sense, they're sort of on topic, they don't go anywhere. On the other hand, they are really, really good at summarizing. I actually ran a class this semester where some of the assignments, the students not only allowed to, but encouraged to use ChatGPT or equivalent, as long as they reported it and told me. And a lot of them did stuff like include their prompts and how they engineered them. And I assert that it was probably the most useful thing I learned in my class. It was a cosmology class. It was interesting. Really interesting stuff came out of it. They discovered stuff I hadn't covered in class, and I went and dug into it. Because the AI was like, oh, if you want to understand dark matter, you should know about the Higgs boson, which does really interesting things. And they were like, and they are useful in some ways already to bounce ideas off. And I can see that becoming a big thing. In science, I think it's going to depend very sensitively on which area of science you're in, whether you're data-driven, theory, proof-driven, trying to find which of the 10 to the 500 theories, the string theory is actually the one true theory. Yeah, they could help that, maybe. And sometimes it provides alternative perspectives. It provides things you hadn't thought of. And that, I suspect, is where the massive productivity growth will be in the future. So here are the great steps in science production, the reporting thereof. Gutenberg, good job. Word processors, I remember when word processors came out. They were so cool. And now ChatGPT. All right, I think where we are going and where we're going to need our, not our guardrails per se, guide rails. I prefer guide rails to guardrails. That was not a typo, that was a deliberate. So AI is going to fairly rapidly help us discover unknown knowns. And in fact, there's actually some serious conversation taking place about this and some preliminary things to basically data mine. My canonical example is find that really obscure statistical thing that somebody came up with, wrote a thesis on, and then nobody ever used it for something, but it's absolutely perfect for solving the Hubble tension or something. And there are large interests with very high interest in finding this on the certainty that some of it does exist. I think the knowledge graph stuff is going to drive us to finding links between apparently unrelated things. They're going to give us teleportation between fields, where there's not a network of ABC link all together, but somebody's like, there's something over there you should know. That's going to be fun. And they're really good at exploring very large data sets or heterogeneous data sets or complex data sets, and either find Arkenstone or summon a dragon and kill us all. Now the question is, are they going to get smart? I don't know. We'll see. But it's conceivable that our AI will actually make discoveries, that it'll self-motivate to go on and explore things we didn't tell it to. And it may find things where we didn't even realize there was things to be found. That's when stuff gets really interesting. There's also some indication already that it's going to come up with new modalities. And my canonical model there for that is the one that learned to play Go and beat everybody. It was doing Go moves that nobody had ever thought of. Like, why are you doing that? Damn, it works, I lose. So the potential's there. Now, we might not just get discoveries, but new ways to make discoveries. And then, of course, if it's a clever AI, it'll use its own discoveries to improve AI. And if we're lucky, we might be able to follow along and see if I understand what it just did to itself. Oh, and then I asked ChatGPT to give this talk for me. It's actually pretty good. It's shorter than mine. So here's the set of slides with a conclusion. That's actually a really good conclusion. All right, here's my conclusion. Having seen its conclusion, I decided to do a different conclusion. AI is a tool. We're going to use it. It can and will be misused. We can try to regulate that, but we can't control it. If nothing else, people just do it because it's funny. It's a Pandora's box, and it's been opened. It needs to be used responsibly. I'm not convinced that there's a consensus as to what actual responsible use is. For example, I'm not sure that Palantir has the same concept of responsible use of its AI tool that it just announced a week or two ago, after the New York Times leaked it. But it's there, and it's doing stuff. And we're going to have to talk about it a lot. I hope that it does some good. And well, we live in interesting times. And I think there's still time for panel. Maybe a question.
Okay, so while we set up the panel, is there a question for Stein? Stein's going to be on the panel as well, but you know, you can. Is there one online or people saving it for the panel? Okay.
Yeah.
Okay.
So I've seen some discussion about AI tools that can categorize texts as either AI generated or human generated. And I haven't been very reliable.
So the most common one is the perplexity score. That's like what ZeroGPT uses. Basically, the success of ChatGPT 3 is it's finally scored low enough on perplexity that you have a hard time telling. And that's improving very rapidly. And we looked at it and looked at the trends, and we didn't even bother putting in a perplexity thing. I mean, we have a perplexity tool we run externally if we want to, but it's not, we don't think it's useful anymore. We already lost that game. OpenAI is looking at watermarking using method. I think they're working on the method the Jan LeCun suggested a couple of years ago. That works unless somebody knows the watermark is there and wants to mess it up badly enough you can't see it anymore, which you can do relatively straightforwardly with medium-sized or longer text, is my understanding. We're keeping an eye on that. We're thinking about it. I don't know if it's going to work, but if it works, we'll try it.
So when you mentioned that there was the first AI generated archive, how are you?
We have multiple ways of detecting it. I wasn't kidding about the Twitter too. Once we see them, it's easier to find them. But as they get better, it's harder to find them. And we're worried that we're already leaking. So yeah, security through obscurity doesn't work, but we use heterogeneous methods.
Okay, thanks, Dan.
Okay.
So we're going to set up a panel at the front, I guess.
Question is, so the first question is open to all, so it's kind of an opener. So it says, with respect to AI advances, what are some good ways for those in the natural sciences to help safeguard their futures in their fields without defaulting to limiting, blocking AI use? Let's start with Professor Tafti. Anyone?
Okay. Well, I don't know if this is on. I think it's like how, I mean, say what I think about any kind of modern or novel AI. I think it's good for doing kind of assistive tasks. So leveraging it in that way, using it to do when it can things like summaries or idea generation. My friends use it for like paper rewriting. So like, they'll want to rephrase something into more formal tone or more scientific tone or think of a different way to say something. So I think for things like that, it can be very useful. Personally, I haven't used it in my writing because I'm very picky. But I think so using it for things that it's like demonstrably good at and not thinking that it's going to replace you. I mean, I don't see AI replacing grad students. Like, they're pretty important to the scientific enterprise. So I wouldn't worry about it too much, honestly, right now. But yeah, thinking about tasks that it can reliably do well is one thing. And then also, I think some of the stuff that I mentioned in my talk, like thinking about what kind of new questions we get to ask now. Maybe there are things that we couldn't address with the existing scientific methods, or there's interesting science questions like about AI that we can ask. So trying to, think of opportunities that come, but I don't see it as that risky to grad students right now.
I would like to add something to this conversation. So number one, I would say similar like what you said. So I believe we and our machines, we should work together. So either as a assistive device or collaborative, kind of activity, something like that. So the other thing is that at least in healthcare community, so people 5 years ago, 6 years ago, they believe that we can, or AI will replace radiologies after 5 years with the advances in AI components and computational orthopedy, for example. But look where we are at. We cannot replace radiologies with AI. So in summary, I would say, so AI and people, or human and people, we can work collaboratively towards a better world.
STEM students, STEM researchers, we are good in math, in logic. These are the things that ChatGPT is not good with, but large language models are good with language, and many STEM students, they are foreigners. They may have less capabilities in terms of writing in English. I feel like this is an opportunity for using LLMs to their advantage. But yes, I agree that there are limitations to this. I am a foreigner. I grew up in Europe, came to the US a few years ago. And sometimes I try to use ChatGPT to rewrite my things. It was sometimes helpful, but in the end, I feel like it's just, I'm also picky, A, and B, it takes also a lot of time to just put it there, wait for the response, put it back where I want it to be, the text. So I feel like until LLMs are more integrated in tools that we are already using, like Overleaf or things like, text editors we are using for writing. So essentially, I would love to use ChatGPT as a kind of Grammarly tool, rather than my AI assistant. I think this is how that would be useful for me, and I think maybe that would be also useful for other people in STEM fields.
Ima, you want to take that?
I can just add a comment to that. So I think I'll talk a little bit more broadly about, large language models per se, since other panelists have already touched upon ChatGPT, and of course, it's sort of help with writing and so on. So one of the interesting things when we think of the features of these kinds of large language models is something called as in-context learning, which is you don't really need to train a model. For example, you don't really need to run a gradient descent algorithm, build a model, and so on. And we can instead provide input-output pairs as samples, as inputs to these models. And they're somehow able to sort of, figure their way out about the tasks that we are asking them to do, and then, sort of make appropriate predictions. So I think it could be interesting to sort of explore that feature or that kind of new learning paradigm that these models offer, with several things that come up in the context of natural sciences that are currently done using things like just building deep neural net models or graph neural nets and so on. So I guess, sort of my high level point here is that I would also advise people to play with these models a little bit more and figure out ways in which they can do tasks that they typically do in certain ways in a more innovative and efficient way with these models as well. So I think there is a lot of scope to sort of apply these models to the classic prediction problems or other kinds of problems that arise in natural sciences. For example, there are teams in Harvard Medical School thinking about using language models for drug repurposing, right? Because these models are technically sort of universal predictors, if you fine tune them well enough, or if you sort of provide enough data about a specific task. So just that exploration could also yield a lot of new developments from the perspective of your own field and your own research. And, coming to the question of, are these going to sort of void any professions? I think I agree with some of the other panelists' opinions that I think there is still a long way to go, and we are still in the human AI collaboration and how to do that effectively, figuring that out phase.
You should be aware of what new tools there are that are relevant to your field. Tools that maybe you're not aware should be relevant to your field. See what people are doing with them and follow along. And some of you should be trying stuff out first. See if you can get new stuff done, but not too much. But real work to do also. And keep learning. Don't freeze your technique or your approach to science.
Yeah, thanks so much for all the panelists for taking that question. I guess it makes sense to throw it out to the audience here for a question, if anybody has one.
Yeah, thank you so much for the presentation overall. I guess my question is mostly to the Professor Tufte about the wearable devices and how they leverage AI models. I think Apple just announced they're building a continuum building this Quartz subscription-based platform that will analyze data from your voice and will be able to predict how the user feels. Just curious, how the medical community thinks about this, big tech stepping up into this medical field, and how reliable it is, and how big consumers be worried about this at all, because this is really exciting, for me personally. Yeah, thank you.
It's actually a great question. Recently, there has been a lot of research activities in wearable devices in different clinical settings, But one thing I would like to highlight in this context is actually privacy, because no matter about, I mean, they are doing good in terms of performance, they're doing good in terms of collecting multiple data sources, diverse clinical data sources, diverse patient data. But one thing comes to consideration is actually privacy and security of our patients, of the people. So generally speaking, majority of our patients, they don't like to share their data with third parties. Doesn't matter, it's Apple, it's healthcare provider. So of course they can collect data, they can harness data, but it would be great if we can come up with some sort of privacy preserving computational methods. Just for example, if you look at some of the works done by Stanford Computer Vision Laboratory, you can see that instead of using wearable device, in which they are somehow annoying, so, but that research laboratory, they are utilizing thermal camera, depth camera, in which they are also offering privacy preserving AI methods to do some sort of data analysis for our patients.
Great. Thanks, Ahmad, for that. I guess we can go back to a question that was submitted by attendees here. The question reads, with the potential for widespread of use for use of AI for generating content and information, we could quickly reach a tipping point where the majority of our online information is AI generated. Is there a danger of sort of an inbreeding and this creating this weird feedback loop in training these models? And is there a risk of perpetuating the same biases on and on? I guess any of the panelists could take the question.
So 3 months ago, I tweeted that we needed to treat data generated before the 1st of December 2022, like the German Navy and wherever it is in Scotland on the bottom of the sea. It's pristine, uncontaminated data that needs to be kept separate from later data. We've already contaminated the discourse, but I don't know if it's going to converge to something or if it's going to go into some sort of chaotic, crazy state where AI is feeding itself and going insane. It'll be interesting to find out.
Yes, so I just wanted to point that I think the current iteration of AI, maybe it was trained with good high quality data, and even though still hallucinates, lies, and so on. So I'm not sure whether the problem is in the data or whether it is in the current generation of AI models that may need to evolve first. We need to make it better at retrieving truthful information. And then once we get there, maybe we will start worrying about the quality of data. That's my perspective, but of course, I think that's also a valid danger.
Yep, thanks so much.
Are there any?
Oh, sorry.
Oh, yeah,
Oh,
please
Hema,
go ahead,
sorry.
Hema.
Oh, sorry. I just wanted to add to that I think even, without the advent of these large language models, which are sort of, which are probably more slated to drive a lot of the content that is being generated online, despite even if they didn't exist, I think we were still worried about this kind of feedback loop, even with just standalone vanilla simple predictive models. And there the feedback loop was that we kind of know humans generate a lot of decision-making data, and they might be biased. And if they are biased, then the models that are sort of built on top of such a data could be biased. And that problem has still existed in a different way, with standalone predictive models, right? And I think that's where the importance of auditing becomes pretty clear, because I think no matter what is the source of the data that these models are being powered by, whether it is data that they generate themselves or whether it is data that's being generated by humans, I think in either cases, there is a risk that you'll run into the scenario scenario where the biases that are somehow tapped in the data are being sort of used by these models and amplified. So I think auditing tools are very important in order to first identify existence of any such biases and then figure out better ways to address those biases, either through data or through training these models in a different way and so on.
Right. All right. Thank you. Are there any contributions?
Hi, thank you so much for the wonderful discussion so far. My name is Harrison. I'm a graduate student here at CMU and I work at the Block Center. And one of the things we're really curious there is sort of the first order educational implications of AI right now, and then the spillover effect into the workforce. And so my general question is more like, what is going to be the desirable traits or skills of people in the future that will allow them to succeed in the classroom and then excel in the workforce?
Does anyone answer the question? Volunteer.
So maybe in terms of developing coding, I think it's becoming important to use tools like Copilot well, I think this is a good tool maybe for learning how to code and potentially for getting used to the kind of code a given company is developing. So I feel like this is maybe one potential way in which large language models will be influencing what people put on CVs and their preparation to the workforce. Yeah, I think that's I would say the main point I wanted to make.
I think something that's very important is the same thing that was important in education before ChatGPT, which is critical thinking, right? And being able to process information from different sources to evaluate where your information is coming from, the validity of sources, and like that is probably only more important now. So I think like definitely using, I've been reading some stuff coming out recently, right, about using ChatGPT as a tool for critical thinking education and like, why would it write, an essay like this to a prompt like this? Like, do we believe these arguments? Can we validate the sources that it's using? So I think that remains like the most important thing in any level of education. And the other thing I would say, like, not to be too like depressing, but a lot of the work I've been doing recently is like focused on like the financial and like societal context of these models. So I think like an even more important question than what skills do we try to build for ourselves to like keep companies from automating us is like realizing that companies are going to try to automate anything they can in order to save money. And so how do we push back on that? How do we say that like, oh, like, I don't know, my very pessimistic view is that, yeah, it's going to replace a lot of things, not because it actually can, but because, it's close enough that we can say, well, we're going to save a bunch of money by replacing this person with AI, and everyone will just deal with everything being a little shittier because we've replaced it with an AI that can't actually replace the human. So I think another side of this is, right, how do we push back on the idea that all of the things that we do are automatable? And I think that's equally important discussion to have. Yeah.
All right.
I would also encourage you. So I do have a couple of suggestions towards your career development, professional career development, things like that. So first of all, I would suggest take a niche. You know what I mean? So define a specific area for yourself. Perhaps if you cannot define it at the moment, so let's say in next year, in next few months, you can define a niche for yourself and be specific for that niche. For example, when I was starting my career, I was saying to people, so I'm a computer scientist. I got all of my degrees in computer science with a specific attention in AI. But after that, I saw that it's not good enough to make a career. Then I delved into the detail of computer vision. So I am now imaging guy. So then I delve into more detailed medical images, not generic images, right? And then got a niche, a specific niche, ortho images. And in ortho, again, total knee replacement, total hip replacement, down the road. So I would strongly suggest you to define a niche for yourself, right? So the second thing I would say is to try to engage a leadership role in your area. Try to attend in actually reputable conferences, right? Try to read like prestigious journals. So what's going on, for example, in Nature Medicine, right? What's going on in Frontiers in AI or Frontiers in AI in Medicine. Every single week, we have to read, a list of papers or at least a couple of papers coming to our community. So, and of course, programming skills is a great help. So programming in Python, programming in, R or those kind of things, it would be a great help. And the last but not least, try to make a broader collaboration. Broader collaboration is starting first with your professors, and then across different schools, across different universities at CMU, for example, as you are saying, you are at CMU, and then extend this collaboration across different schools nationwide and then worldwide, and you will get there.
All right, thank you. So we should move on to the next submitted question. So this person asks, I am fairly skeptical about explainability these days, particularly as our models get in the billions or more parameters. What are the current thoughts on whether it even makes sense to say that super large models with emergent behavior can be made explainable to us? So Anna, do you want to start on that?
Yeah, I guess so. The reason I was interested in this question in particular is I think there's already an assumption happening there that there are emergent behaviors coming out of any of these models, which there very well could be. I'm not going to take too negative of a stance on it, but we don't know that there are, right? Anything that people are talking about as emergent behavior, theory of mind, mathematical reasoning, we really don't have any substantial evidence that those are happening because we don't have any tests for them. So I think that's one thing I would say in regards to explaining large language models is how do we need paradigms for how we even evaluate these things, right? And a theory of mind test that we use as psychologists on 7-year-olds in a 3D environment where they can actually interact with physical objects, just turning that into a text-based question is maybe not sufficient for testing theory of mind. So working interdisciplinary, coming up with different evaluation techniques. And then I think a lot of the stuff I mentioned in my talk is also I think very relevant and useful for this, right? How do we start to build more of a model of how machine learning works? And I think that involves some amount of observational study, but it can't stop there. We're kind of stuck on just observational study. I saw ChatGPT do this once or even 10 times, but what if you vary the prompts or you vary the sentence structure things? We need to come up with ways of systematic study and then try to push that into some kind of general model type results we do with other kinds of systems that we try to understand. In terms of explainable AI techniques, yeah, I don't know that that's useful for super large language models. I think they are used, they're certainly useful. Specific models, and I also don't think we should be using large models to do specific decision-making tasks. We probably shouldn't be trying to use ChatGPT to make a recidivism prediction or something. And so traditional XAI techniques would be very helpful there, but SHAP is probably not going to explain GPT-4. Yeah.
All right.
Sorry. Hima, do you have any thoughts on that?
Yeah, I can add to this. So I think there are a few points that I want to highlight, and I think Savan has already done a great job of summarizing some of the key things there. So first of all, I think the explainability, I think it's not driven by the fact that we can or cannot explain a model. It's driven by the applications in which the models are being employed, right? So if you are deploying a model in an application where that kind of transparency or understanding is important, then it's, then we are stuck with the question of, okay, so what do we do about explaining this model, right? So I would think of explainability being driven by the context more than our ability to explain something or not, right? The second thing is, while the existing methods, like if you were specifically talking about post hoc explanation methods like LIME or SHAP or gradient-based approaches, sure, they may not be able to be like vanilla sort of applied to these larger language models, but I think there is scope for sort of thinking about new techniques there in terms of understanding larger language models. So for example, these models already do generate some kind of chain of thought rationales. Of course, it is questionable whether those rationales is how exactly the model is thinking internally, or if the model is kind of just putting that out to help a human just trust it more, right? So those questions are still unanswered, but I think there are other different techniques and approaches that will follow through to help us understand a little bit about what these models might be doing, right, going forward.
Thanks. Yes,
So, yeah, so just to add to this a little bit, the explainability techniques like SHAP, LIME, I think they can, at least SHAP can be used to explain decisions of a text classifier. Of course, LLMs are not text classifiers, but you could ask them a question that is kind of going in the direction of text classification, yes or no, or, tell me what category of thing is this, predict recidivism. I don't think it's a good idea, but we could try to explain them. I think there are ways to do that. And whether there is a convergence, I agree that the field of the explainable AI field is still developing, and that's a very good thing. I think there will be convergence. I think there are already strong candidates. There are already many discussions among researchers which of the explainability measures is the right one, according to some reasoning. So yeah, I'm positive about this, but I also agree that this is an active field of research, so it will take some time before we converge.
Great. Yeah, thanks to all the panelists for that. I guess we could change the tone a little bit. There was an interesting question submitted to us. The question reads, how natural scientists can help achieve responsible AI? What researchers in the basic sciences, how can they contribute? I guess it's a question for everyone. I guess we could start with Stein.
Well, from what I know of my colleagues, I'm not sure we're going to be all that helpful. We're more likely to be the ones who go, cool, new toy, let's see if we can blow something up. So I'll defer to my fellow panelists.
When could like uncertainty quantification methods be like uncertainty quantification methods that are used in physics could it be helpful in some way? Anybody?
I mean, yes,
Yeah,
well,
please.
yeah, I said that in the talk, I think, yeah, so I think there's several things like yeah, my whole talk was kind of about how scientific principles can help with responsible AI. So I think like, yeah, a lot of that is worthwhile. Of course, it's not the full solution, right? Like, I don't think any of these problems are purely technical. And so that's only going to get us so far. And I think it's also extremely important that natural science students take non-science classes. This is like my other big soapbox is I think liberal arts education is extremely important, and we need to be educating our students better, because otherwise, right, we just end up doing a bunch of stupid stuff that if you had ever talked to like a social science researcher or a gender studies person or like anyone who thinks about the history of power in the world, like they could have told you that it was a bad idea. And we could avoid a lot of things if we just had like slightly more interdisciplinary education. So yeah, try to take some more classes, challenge the way that you think, try to do interdisciplinary projects if you can. Like, I think those are all great tools. And then, yeah, I think there are on the other side, like I said in my talk, trying to be more precise about how we think about and more critical about how we think about AI and evaluation of both the models and their impact.
Anyone else? Anyone else? Maybe in
I
the
can add
audience?
just a bit. So I think just adding upon the prior point, I think where folks and researchers from natural sciences, or for that matter, like any other domain beyond machine learning, can be helpful is with use cases and stress testing of any of the latest AI ML tools that are coming out and that are being sort of like thrown at them saying, here is yet another new cool tool, right? Oftentimes, I think when it comes to at least the work on explainability, like several of the algorithms came up as a consequence of those use cases being flagged by researchers in other domains, and highlighting what is going wrong with the way they are using machine learning models and so on. So I think stress testing and use cases is where, folks from other fields can also like very directly contribute to extending the literature on responsible AI. At least, of course, a lot more too.
Great, thanks.
Anyone in the audience? No? Yeah.
Yep.
Hi, your talks were all really great today. Thank you. So I kind of have a question from the science side. I'm in material science, and one of the questions we often get is how might we replace like physical models with AI and ML? Because AI and ML is like a lot faster, but we can't always explain how it gets there. And there's been some kind of conversations about this today. But do you think that we'll be able to ever replace physical models, or is it going to always just kind of be this balance of physical models and AI and ML just to kind of speed up certain parts of it?
I think there are, I don't know if there's, okay, well, so I'm from particle physics, so we have a little bit of a different like modeling paradigm, but I think there are certainly ways to like at least augment or replace part of our physical models with AI models. So we, in particle physics, we do a lot of simulation, and there's been a lot of work in the last like 5-6 years using instead of like a first principles physics simulation, can we do part or all of that simulation chain with AI? And I think the explainability part of it is not so important. It's the fidelity. And so if you can come up with enough tests that you can convince yourself that it is capturing all of the different effects you would want to see, that it is that all of the different distributions look right. And, in some cases we're seeing that you can, in some cases we're seeing that you can't. There's also really interesting research, particularly from like DeepMind, about different kinds of physics simulators with AI and ways that you can incorporate physics knowledge into these kind of models. So you don't have to start from scratch and ask it to learn all of the physics principles. By being creative in how you design your simulator task or your loss function, or the architecture of your model, you can incorporate like some physics constraints directly into your simulator, your physics engine, or whatever you might be wanting to build. So I think there's a lot of cool possibilities there. I don't know if like all of our physical models are going to be replaced by AI, but there's definitely potential for some utility. Yeah.
All right, please, Stein.
Shirley Ho and collaborators have been doing some of this at Flatiron and gotten some interesting results, including discovering, as I recall, emergent physical law from basically raw data. I think we also have to worry a little bit about whether, essentially for the most part, what we do is we just linearize the universe. We do perturbation theory and do Taylor series expansions, and it works. It's awesome. And then, we throw in the Lagrangian, we get conserved quantity symmetries, and it may be all completely fake. And maybe AI will give us true reality of the universe. And we were just doing an approximation of physical theory. But I'm not betting on it, but It could be.
All right, thank you. So we should move on to the next contributed question. So how universities should handle the impact of AI in academic and research integrity? Professor Tafti, do you want to take this?
So in terms of integrity. So I think, at least in terms of research integrity, I would say, so there would be a couple of strategies to at least investigate and come up with an idea for research integrity in AI. So I would say perhaps make a broader team, across with different expertise, with different skill sets, and multidisciplinary team in which they do have a list of expertise they can share, they can talk, they can collaborate together. So it will help research integrity in AI, I would say. So the second thing is that we can embed this kind of integrity with other functionalities. For example, if our universities can get together and come up with a generalized AI consortium, let's say, for example, if they can share data, if they can share model towards generalized AI, not just specific, sort of AI in a specific kind of domain. So let me put it in this way. Imagine we want to make a model to classify some sort of radiography images and come up with some ideas. Let's say, for example, this plane radiograph does carry some sort of bone lucency or things like that. So one way to make a model is to utilize, for example, UPMC data, right, to develop a model. But if we only use UPMC data, the model we will be generating is just biased to the amount of the data and also to quality of the data we have at UPMC. So it doesn't cover that much diverse patient, right? But if we can combine these data with, I don't know, like, Philadelphia Hospital, with Mayo Clinic, with Marshfield Clinic across our nation. So the data in terms of quality and quantity is going to be more appropriate to feed to machine learning or deep learning models. From other side, the model we will build is going to be more generalized model. So it will enhance fidelity, reliability of the model. It will enhance scalability of the model. It will improve availability of the model. And yeah, that's one strategy I would suggest.
All right. Anyone else on this question? No? All right. Let's move on to the next one, Kasim.
Sure. Actually, I have a question. So in Savannah's talk, she mentioned touched upon slowing things down, and we do hear that a lot these days in terms of publishing, in terms of research moving forward in AI. What I would like to hear from all of you, if we have time, is what specific things do we need to put in place once we slow it down? What are the checks that we need to put in place? What are the things that we need to implement in the publication processes? What are the things that we need to put like checks and balances that we need to include in order to get the necessary effect of slowing things down?
So there's kind of two thoughts I would have for that question. So one is like things that we can control, which are things and structures within the research community. So I think a lot about publishing and the kind of publishing structure and norms that we have in machine learning in particular, this very conference-driven, benchmark-driven paradigm that we have right now. And I think there's several things, and some people are really looking at experimenting with different publishing paradigms. So there's this group, I Can't Believe It's Not Better, that has run a few workshops at conferences, and they run a talk series online. And this is like a retrospective series where you look back at papers that you've published in top conferences before and explain like why they actually are not right, or you wouldn't do them the same way again, or things like that. So having more opportunities for things like that. People have also looked at pre-registration, which I think could be super useful, where you say, okay, I'm going to do this study and I might not get state-of-the-art results, and we're going to publish it anyways in this workshop or this conference or this journal, whatever. I think that would go a long way too, because like something that I think is a big problem right now is you can't publish negative results. Like that's just, if you don't get SOTA on some benchmark, like you're not going to get accepted. And while of course it's interesting to see how things improve, it's also interesting to see what doesn't work, because, you know, like I keep saying, we have no real model of how this stuff works. And in order to get a real model, you need to know when it works and when it doesn't work. And if we only know when it works and we're cherry picking examples and we're, you know, fiddling with all of the hyperparameters so we get, you know, 0.5% better performance, and then NeurIPS takes our paper, like that's just not like super useful to me. So I think, yeah, looking at different publishing paradigms, you know, selfishly, I also think the whole conference instead of journal thing is a little frustrating, because you are on these weird arbitrary timelines to publish, and that also kind of impacts how people approach the work. And we actually have a paper also about dealing with some of the like corporate impact on research publishing. So calling for things like, you know, requiring companies who publish at research conferences to say like, this is what our internal review process is like. This is the scientific checks that we do, because we saw with like a bunch of the Google ethics team stuff, like it's very not clear how their scientific review happens. So also making that more clear, so we have more trust in the research publishing ecosystem. Yeah.
Hima, any thoughts?
So one thing I would like to add to what Savannah was just mentioning is I think it's a bit of a game of incentives, right? So I think, you know, I personally believe that it would be hard to put your incentive structure in a certain way and then say, you know what, I'm still going to put some checks and balances so that these things are not going to happen. Like, I think probably a more workable approach is align your incentives to what you want the behaviors to be, right? So for example, if you want everybody to slow down, make sure that there is no incentive to publish like X papers an year, and that's not glorified in any manner, whether it is in, you know, promotions, whether it is in like, you know, invite any of those, right? So I think those incentives somehow need to align with the behaviors that you want to see. Until that happens, I think this will always be a shaky territory.
All right, please, yeah.
I totally agree with Hima's point, and also with Savannah's point earlier. I think just recently there was a blog post from ICM. ICM is like the a major computing organization organizing many of the top conferences in computer science, and the title of the blog post was ACM for Public Good. So there is this possibility of kind of pushing computer science research more towards public good. I think that it's like a wonderful idea. And similarly, I do think making computer science research more interdisciplinary, connecting with domain experts, with social science research, with society, I think this is crucial to make our to make this technology more capable and useful broadly in a good way to the society.
All right. Okay, so yeah,
Yes.
please go.
Publishing negative results is critical, and that has to be incentives that be provided for that. But that'll speed things up. It'll eliminate dead ends. The incentive structure is to publish a lot and publish fast, and it's a perverse incentive. But it goes in both directions. It's not just the researcher being incentivized, it's the people putting the stuff out are incentivized. you can't slow it down. And also, there's a big world out there that's not the US. Yeah, if the US slows down, other people will be very happy to take comparative advantage. We're in a red queen race, the stakes are really high. And right now, with things changing very rapidly, comparative advantage is massive for the people who get there first. And until that changes, until there's a plateauing or some major incentive structure change, there's no slowing down.
Yeah, please, Przemek, do you want to
So-
respond? That's not my perception. I feel like people in Europe, they would be very happy to slow down. Honestly, they want to slow down. They want to work 4 days per week. Here in the US, you barely have any holidays. People work on Saturdays, Sundays. That's just normal here. I think the world wants to slow down, and my impression is actually that this US driving that, and that maybe because US is kind of feeling like that everything is danger around it. It's in danger maybe of losing its position worldwide. Maybe because of this, it is trying to be as competitive to the extent that is kind of maybe bringing not the best effects. But I don't know. It's of course in judgment call. I think this is very hard to judge in general. So,
but there's still an even bigger world out there. And there are a lot of incentives in a lot of places to go fast and get ahead.
Yes.
But you can leverage
Right.
to like make excuses for doing harmful things, right? We have this whole like, oh, specter of China is going to beat us in the AI race to like, what technology are we even trying to build, right? There's no specific end game in the AI race, but they're going to beat us and we're better and, you know, we're democratic and they're authoritarian. So like, no, it's totally fine. Like that justifies everything that we're doing. Like, I do agree. There's a whole world out there, but also people definitely leverage that narrative to like support what they're doing in a way that is maybe not totally justified.
All right.
There's a very instructive metaphor in the past, or an analog for the current situation in the nuclear arms race. People went crazy. You have no idea how many nuclear bombs are built or what we can build. But it did slow down eventually. But while it was in the upswing, there was no slowing it down.
all right. It's me that I really believe that there should be stronger international institutions to control nuclear weapons and to control AI in future. That's my opinion.
All right. Thank you so much for the panelists. So we will have our last closing question now, and this is my favorite. So this one reads, human brain is not explainable or responsible. So why should AI be explainable or responsible? So please, does anyone volunteer?
So I think short answer is because probably we want to live in a better world.
This is also sorry. This was also my favorite question. And I thought a lot about my response to it, which is basically like, yeah, sure, we don't know how the human brain works from a, physical to meta level. But we don't let a human randomly run everything with like no democratic process or no oversight, right? So it's not really a fair parallel that's being made in this question, in my opinion. Like we wouldn't replace okay, so we think about maybe replacing a judge with AI or something, right? But a judge goes through extensive training, different approval processes, bar exams, there's oversight, there's like a whole system set up around decision-making processes that we have in the world right now. And yeah, they're not always great and they're not always fair. But we don't just go like, okay, yeah, like you can control everything, right? So I think, right. The way that we're framing AI is not at all how we frame humans. And so we maybe don't need to explain every single thing about it, but we also shouldn't put it in positions we wouldn't put ourselves in.
All right, Stein, please.
We should ask AI. When they can explain itself, then we know we're there. Maybe they can explain us too. That'd be really interesting.
Yes, I agree. Hima, do you want to take
Yeah, I just
all
want
right.
to chime in with a couple of points. So one thing I think is, first of all, like one of the assumptions in that statement is humans are not explainable, we are also not responsible, but I don't think that's necessarily true, right? When something goes wrong, doctors are held accountable, judges are held accountable, all these people are held accountable, and they're supposed to submit post hoc explanations, though whether that's the truth or not, and that's the real ground truth of what a human thought process is or not, that's a separate question. But they still need to sort of explain their side of why they took certain actions and what were they thinking and so on, right? So in that sense, humans are still accountable. They need to provide explanations when things go wrong. And on top of that, I just want to add to the point that Savannah was bringing up just a bit ago, which is that, so with a human, a bad judge or a bad doctor can cause a certain degree of harm. But the whole point of going towards AI is to sort of use these tools at scale and standardize everything and employ one model to make decisions, widely, right? So across a country or maybe even beyond. So if that's the kind of impact one model or one algorithm is going to have, then it should be subject to much harsher checks than an individual human would be subject to, because now, you're screwing up the whole decision process of the entire country if this goes wrong.
Please.
So personally, a little bit concerned by this question, because as Hima truly mentioned, so we are all responsible for what we are doing. So, and then very simple example, when I'm talking to my daughter, I should explain. So, I should provide her with explainability. So why I am saying this, why I am, coming with this kind of decision. So, and in terms of responsibility, we are all taking, responsibility. So the question is a little bit confusing to me, actually. Yeah. And from other side, so today we have seen a lot of examples, just few examples by Hima. So when she said, so there is a judge, so if the judge or AI comes with some sort of, prediction for a defendant, so that results should come with explainability. If we turn it into real judge, not judge with the use of AI, so the judge should also, or will not should, will come with some sort of explanation based on policy, based on law, based on whatever. So yeah, I'm concerned with this question.
Yeah, Hima could.
Statement. So the answer to that question is that it is dependent on the context. Can you outline what you would need to answer the question? So I believe the question is like bad framed, right? But it is a very hot one. So it's like you were trying to say that there's no context, there's no direction, there's no rule. What would you like in order to answer the question? What do we? So I'm trying to formalize how you would formalize the question.
I do formalize the question.
So you cannot answer to the question as it is, and you're concerned with that. So what?
So I'm not saying I cannot answer to this question. I'm saying I am a little bit concerned to the idea of this question. So the question is saying, if I'm not mistaken, the question is saying why why AI should be responsible, should be explainable, while we are not. Is that right? So, and I'm saying we are. Not we are not, we are. So imagine, for example, yesterday I was talking to my daughter. She wanted to have a surgery, to get a surgery for whatever purpose. I was telling her, so you should wait for a couple years and then do the surgery. And she asked me why. So that's where explanation comes in, right? So, and then I said, so I talked to a couple of my friends, they are surgeons, they are working at Mayo Clinic. So they came with this idea, and this is a reference, and it has been already around the community for several years. So this is the reason. So I'm challenging this question with my idea, saying that we are already responsible. we as human, and we are providing explainability for majority of the tasks we are doing, right? So that's the thing I'm trying to say.
Stein, please.
You don't actually have to be a lawyer to be a judge. In fact, the Supreme Court of the United States has had a Chief Justice, a lawyer. Also, explanation in medicine is very privileged. If you're educated and know to ask and have friends who are doctors or relatives, you get a much better explanation than if you're a random person off the street. So there's an ideal concept that, for example, medical people should explain why things are being done, but a large fraction of the time they don't. This needs to be done, we're going to do it. And they use an authoritative position. So we have to be careful about taking Platonic ideals of how things should work and think about how they would actually work, partially informed or uninformed population dealing with things, and whether we actually are going to achieve anything like our ideals, or they have to deal with ugly practicalities and things not being the way they should be.
Yes, yes, but I think he must comment that well, with the rise of AI, there is this opportunity to make things better because they just scale, and also they can deliver the same solution, so the same explainability to everyone. So I think there is a real opportunity here to make things better. I think we are just making first steps. This is maybe baby steps towards a certain direction. It will take a lot of time, but maybe, hopefully, we'll get there.
All right. Is there any other questions from the audience? Should we close the session at this point? Yeah. All right. So thank you for all the panelists for answering the questions and contributions from the audience as well.
Thank you.
All right. So the food is here, so it's party time.